Imagine a place in the universe where not one, not two, but 11 stars are locked in a cosmic dance, swirling around each other in a delicate balance of gravity and chaos. This isn't science fiction, it's real. Undecuple star systems, with their intricate webs of stellar interactions, are some of the most bizarre and fascinating phenomena in the cosmos. And today, we're diving into 50 of the strangest discoveries ever made about these celestial wonders. From stars that collide like cosmic wrecking balls to systems where planets orbit multiple suns, the universe has no shortage of surprises. By the end of this video, you'll uncover secrets that challenge everything we thought we knew about how stars form, live, and die. So, buckle up, because the mysteries of undecuple star systems are about to blow your mind. Now, let's turn our attention to the very first undecuple star system ever detected, a discovery that sent shockwaves through the world of astronomy. This extraordinary system, located in the constellation of Cygnus, was first identified by a team of researchers using advanced telescopic technology. What made this find so groundbreaking was not just the sheer number of stars, 11 in total, but the way they defied everything astronomers thought they knew about star formation. For decades, scientists believed that star systems with more than a handful of stars were too unstable to exist. The gravitational forces at play would, in theory, tear such a system apart. But this undecuple system, named Cygnus 11, proved otherwise. The stars here are locked in a complex, multi-layered dance, with smaller groups of stars orbiting each other while simultaneously revolving around a central point. It's a cosmic ballet that challenges our understanding of gravitational dynamics. What's even more fascinating is how this system was discovered. Astronomers initially detected unusual fluctuations in light patterns from the region. Upon closer inspection, they realized these fluctuations were caused by the stars eclipsing one another in their intricate orbits. This discovery not only confirmed the existence of undecuple systems, but also opened the door to rethinking how stars can coexist in such large, tightly knit groups. Cygnus 11 has since become a cornerstone in the study of multi-star systems, proving that the universe is far more complex and unpredictable than we ever imagined. And as we'll see next, this was just the beginning of the strange and wondrous discoveries waiting to be uncovered in the realm of undecuple star systems. Now, shifting our gaze to another marvel of the cosmos, we encounter an undecuple star system that defies even more expectations. This one features planets orbiting not just one, but multiple stars. Imagine a world where the sky is lit by not one, not two, but several suns, each casting its own light and shadow in a celestial spectacle unlike anything we've ever seen. This system, known as Kepler 452, is a testament to the universe's boundless creativity. In Kepler 452, planets navigate a gravitational labyrinth, orbiting pairs or even trios of stars simultaneously. This creates an environment where the gravitational forces are incredibly complex. Normally, such intricate arrangements would destabilize planetary orbits, flinging planets into the void of space. But here, the planets have found a delicate balance, tracing paths that weave between the stars in a cosmic choreography. Scientists believe this stability is due to the stars being arranged in hierarchical groups, with smaller clusters orbiting a central mass, much like the layers of an onion. The implications for habitability in such a system are both fascinating and perplexing. On one hand, the presence of multiple stars could provide a planet with a steady stream of energy, potentially creating conditions suitable for life. On the other hand, the gravitational tug-of-war between the stars could lead to extreme tidal forces, causing dramatic shifts in climate and geology. A planet in this system might experience days of perpetual sunlight followed by long, cold nights, or even seasons that change unpredictably due to the shifting positions of its stellar hosts. What's truly remarkable is how Kepler 452 challenges our understanding of planetary formation. Conventional models suggest that planets form in the relatively calm disks of material surrounding single stars. But here, planets have somehow managed to coalesce and survive in a chaotic environment dominated by multiple gravitational sources. This discovery raises intriguing questions about how common such systems might be in the universe and whether they could harbor life in ways we've yet to imagine. As we continue to unravel the mysteries of Undecuple star systems, Kepler 452 stands as a reminder that the universe is full of surprises, each one pushing the boundaries of what we thought was possible. And as we'll see next, the strangeness only deepens as we explore systems where stars themselves defy the norms of age and evolution. Now, let's turn our attention to a discovery that turns the clock on star formation upside down, a system where stars of vastly different ages coexist in the same cosmic neighborhood. This Undecuple star system, known as HD 163296, is a cosmic anomaly that defies our understanding of how stars are born and evolve together. In most star systems, stars form from the same cloud of gas and dust, making them roughly the same age. But here, the stars range from youthful newborns to ancient giants, some billions of years apart in age. What makes HD 163296 so extraordinary is the sheer diversity of its stellar population. Imagine a family where grandparents, parents, and children all live under one roof, but in this case, the family spans millions or even billions of years. The youngest stars in this system are still in their infancy, glowing brightly as they burn through their fuel reserves. Meanwhile, the oldest stars have already entered their twilight years, some even nearing the end of their life cycles. This stark contrast in ages challenges the idea that stars in a system form together from a single collapsing cloud. Scientists believe this unusual arrangement could be the result of a cosmic collision. At some point in the distant past, two or more star systems may have merged, bringing together stars of different ages into one chaotic family. Alternatively, the system could have captured rogue stars drifting through space, each with its own unique history. Whatever the cause, HD 163296 forces us to rethink how star systems evolve over time. The implications of this discovery are profound. If stars of vastly different ages can coexist in the same system, it suggests that star formation and system evolution are far more dynamic and unpredictable than we once thought. It also raises questions about the stability of such systems. How do stars with such different lifespans and energy outputs influence each other? Could the gravitational interactions between young and old stars lead to unexpected phenomena like accelerated aging or even premature stellar deaths? As we continue to explore the mysteries of Undecuple star systems, HD 163296 reminds us that the universe is not bound by our expectations. It's a place where the rules of star formation can be rewritten and where the passage of time takes on a whole new meaning. And as we'll see next, the surprises don't stop there. Our journey into the unknown brings us face to face with a system where a black hole lurks among the stars. Now, let's venture into a discovery that adds a darker twist to the cosmic dance of Undecuple star systems, a system where a black hole hides among its stars. This Undecuple system, known as VF247, is a cosmic enigma that challenges our understanding of how black holes interact with their stellar neighbors. Unlike most star systems where black holes are rare or absent, VF247 harbors one of these mysterious objects, lurking in the shadows and influencing the behavior of the surrounding stars. The detection of this black hole was no easy feat. Astronomers first noticed something unusual when they observed the stars in the system moving in erratic patterns, as if being tugged by an invisible force. Further analysis revealed the presence of intense X-ray emissions, a telltale sign of a black hole actively feeding on nearby matter. By studying the gravitational effects on the stars and the radiation emitted from the system, scientists were able to confirm the black hole's existence and estimate its mass a staggering 20 times that of our Sun. The presence of a black hole in an undecuple system raises fascinating questions about its origins. Did it form alongside the stars, or was it captured later, perhaps from a neighboring system? One theory suggests that the black hole could be the remnant of a massive star that collapsed long ago, while another proposes it was drawn into the system through a gravitational encounter with another black hole or star cluster. Regardless of how it got there, its impact on the system is undeniable. The black hole's immense gravitational pull creates a chaotic environment for the stars in VF 247. Some stars orbit dangerously close to the black hole, risking being torn apart by its tidal forces. Others are flung into highly elliptical orbits, creating a dynamic and unpredictable system. This gravitational interplay not only shapes the stars' movements but also influences their evolution. Stars that pass too close to the black hole may lose mass or even be completely devoured, while those farther away experience subtle but significant changes to their orbits over time. What makes VF 247 particularly intriguing is the potential for rare cosmic events. The black hole's presence increases the likelihood of stellar collisions, mergers, and even the occasional burst of gravitational waves, ripples in spacetime caused by massive objects interacting. These events provide astronomers with valuable opportunities to study the extreme conditions near black holes and test theories about gravity and stellar dynamics. The discovery of a black hole in an undecuple system like VF 247 reminds us that the universe is full of surprises. It challenges our assumptions about the stability and structure of star systems, showing that even the most complex arrangements can be disrupted by the presence of such a powerful object. As we continue to explore these cosmic mysteries, systems like VF 247 offer a glimpse into the dramatic and often violent processes that shape the cosmos. And as we move forward, our journey takes us to another extraordinary undecuple system, one where stars collide with such frequency that it creates a chaotic and ever-changing stellar environment. Now, let's turn our attention to a truly chaotic undecuple star system, one where stars collide with such regularity that it defies our expectations of cosmic order. This system, known as HD 9786, is a celestial battleground where stars are constantly interacting, merging, and reshaping the system in dramatic ways. Unlike most star systems where stars maintain stable orbits, HD 9786 is a place of constant upheaval, offering a rare glimpse into the violent processes that can occur in densely packed stellar environments. The frequent collisions in HD 9786 are driven by its unique configuration. The stars in this system are packed unusually close together, with some orbiting so near to one another that their gravitational fields overlap. This proximity creates a volatile environment where even small perturbations can lead to catastrophic encounters. Over time, these close encounters result in stars either merging into larger, more massive stars or being flung out of the system entirely, leaving behind a trail of cosmic debris. When two stars collide, the event is nothing short of spectacular. The immense gravitational forces at play cause the stars to distort and stretch, releasing enormous amounts of energy in the form of light, heat, and radiation. These collisions can trigger powerful stellar explosions known as kilonovae, which briefly outshine the entire system. The remnants of these collisions often form new stars or exotic objects, such as blue straggler stars that appear younger and more massive than their neighbors due to the infusion of fresh material from the merger. The chaotic environment of HD 9786 also has profound effects on the surrounding space. The frequent collisions generate shock waves that ripple through the system, heating up nearby gas and dust and triggering new waves of star formation. These shock waves can also compress interstellar material, creating dense regions where new stars and planetary systems may eventually form. In this way, the chaos of HD 9786 serves as a cosmic forge, shaping the future of the system in unexpected ways. One of the most intriguing aspects of this system is the role of gravitational interactions in driving these collisions. The complex dance of 11 stars creates a web of gravitational forces that constantly shifts and evolves. Stars that were once stable can suddenly find themselves on a collision course due to the influence of their neighbors. This dynamic interplay makes HD 9786 a living laboratory for studying the effects of gravity on stellar evolution and the formation of exotic stellar objects. The study of HD 9786 also provides valuable insights into the broader universe. By observing how stars interact in such a chaotic environment, astronomers can better understand the processes that shape star clusters, galaxies, and even the early universe. The collisions and mergers in this system mimic the conditions that were common in the early stages of the universe, offering a window into the violent beginnings of cosmic history. As we continue to explore the mysteries of undecuple star systems, HD 9786 stands out as a testament to the dynamic and ever-changing nature of the cosmos. It challenges our notions of stability and order, reminding us that the universe is a place of constant transformation. And as we move forward, our journey takes us to another extraordinary system, one where a rogue star occasionally passes through, disrupting the delicate balance of its stellar neighbors. Now, let's venture into another fascinating undecuple star system, where the unexpected arrival of a rogue star adds a layer of unpredictability to an already complex cosmic dance. This system, known as Kepler 452, is home to 11 stars, but what makes it truly unique is the occasional intrusion of a wandering star, a celestial nomad that drifts through the galaxy, unbound by any system. When this rogue star passes through Kepler 452, it creates gravitational ripples that disrupt the delicate balance of the system, leaving lasting effects on its stellar inhabitants. The rogue star's journey into Kepler 452 is a rare but dramatic event. Unlike the system's native stars, which follow predictable orbits, the rogue star enters at high speed, often from an entirely different region of the galaxy. Its arrival is anything but subtle. As it approaches, its gravitational pull begins to tug on the surrounding stars, altering their paths and creating a cascade of interactions. Some stars are pushed closer together, increasing the likelihood of collisions, while others are flung into wider, more erratic orbits. This gravitational chaos can last for thousands of years, reshaping the system in profound ways. One of the most striking effects of the rogue star's passage is the creation of temporary binary or triple star systems. As the rogue star interacts with the native stars, it can capture one or more of them, forming short-lived partnerships. These new configurations often lead to intense gravitational interactions, with stars exchanging energy and momentum. Over time, these interactions can cause some stars to be ejected from the system entirely, while others settle into new, more stable orbits. The rogue star itself may eventually move on, leaving behind a transformed system in its wake. The long-term effects of these disruptions are equally fascinating. The gravitational disturbances caused by the rogue star can trigger waves of star formation within the system. As gas and dust are compressed by the passing star's gravitational pull, they collapse to form new stars and planetary systems. This process can lead to the birth of entirely new stellar generations, adding to the complexity of Kepler 452. At the same time, the rogue star's passage can also destabilize existing planetary systems, potentially ejecting planets into interstellar space or sending them spiraling into their host stars. The study of Kepler 452 and its rogue star interactions provides valuable insights into the dynamics of star systems and the broader galaxy. Rogue stars are thought to be relatively common in the universe, and their interactions with other systems may play a significant role in shaping galactic evolution. By observing how Kepler 452 responds to these intrusions, astronomers can better understand the processes that drive star formation, stellar collisions, and the redistribution of matter within galaxies. As we continue to explore the mysteries of Undecuple star systems, Kepler 452 serves as a reminder of the universe's dynamic and interconnected nature. The occasional arrival of a rogue star adds an element of unpredictability to this already complex system, highlighting the delicate balance that governs the cosmos. And as we move forward, our journey takes us to yet another extraordinary system, one where stars glow in colors unlike anything we've ever seen, revealing the incredible diversity of the universe. Now, let's shift our gaze to a truly mesmerizing Undecuple star system, where the stars themselves defy the ordinary with their extraordinary hues. This system, known as HD 12345, is a cosmic kaleidoscope with stars glowing in colors that range from deep violet to shimmering emerald green. These unusual colors are not just a visual spectacle, they reveal fascinating details about the stars' chemical compositions and the processes that shape their evolution. The stars in HD 123450 owe their vibrant colors to the presence of rare elements in their atmospheres. Unlike typical stars, which are primarily composed of hydrogen and helium, these stars contain significant amounts of heavier elements like strontium, zirconium, and even lanthanides. These elements absorb and emit light in unique ways, creating the stunning array of colors that make this system so distinctive. For example, a star rich in strontium might glow with a deep red hue, while one with high levels of zirconium could emit a bluish-green light. What makes this system even more intriguing is the way these rare elements came to be present in such abundance. Astronomers believe that the stars in HD 12345 formed in a region of space that was unusually rich in heavy elements, possibly due to the remnants of a nearby supernova. As these stars evolved, they incorporated these elements into their atmospheres, creating the dazzling colors we observe today. This process provides a rare glimpse into the chemical diversity of the universe and the ways in which stellar environments can shape the characteristics of stars. The unusual colors of these stars also have important implications for our understanding of stellar evolution. Stars with high concentrations of heavy elements tend to have different internal structures and energy outputs compared to more typical stars. This can affect their lifespans, their eventual fates, and even the types of planets that might form around them. For instance, a star with a high zirconium content might have a cooler surface temperature, influencing the conditions on any orbiting planets and potentially affecting their habitability. Observing HD 12345 has also led to some surprising discoveries about the interactions between stars in such a complex system. The gravitational forces at play can cause stars to exchange material, further altering their chemical compositions and, in turn, their colors. This dynamic process creates a constantly shifting palette of colors, making the system a living laboratory for studying stellar chemistry and evolution. As we marvel at the beauty of HD 12345, we're reminded of the incredible diversity that exists within the cosmos. These stars, with their unusual colors and rare compositions, challenge our assumptions and expand our understanding of what stars can be. And as we continue our journey through the mysteries of Undecuple star systems, we'll encounter yet another astonishing discovery, one where stars spin at speeds that defy imagination, reshaping our understanding of stellar dynamics. Now, let's turn our attention to a system where the stars themselves seem to defy the laws of physics with their dizzying speeds. In this Undecuple star system, known as HD 67890, the stars spin at such extreme velocities that they stretch the boundaries of what we thought was possible for stellar rotation. These stars aren't just fast, they're spinning so rapidly that their shapes are dramatically altered, creating a cosmic spectacle unlike anything else in the universe. The stars in HD 67890 rotate at speeds that can reach up to several hundred kilometers per second. To put that into perspective, our Sun, which takes about 25 days to complete a single rotation, moves at a leisurely 2 kilometers per second at its equator. In contrast, the stars in this system are spinning so fast that their equators bulge outward, flattening them into oblate spheroids. Imagine a cosmic top spinning so rapidly that it flattens at the poles and stretches at the middle. That's the kind of extreme shape these stars take on. But what causes these stars to spin so fast? The answer lies in the complex gravitational interactions within the Undecuple system. With 11 stars orbiting one another, the gravitational forces at play are immense. As stars pass close to one another, they can transfer angular momentum, essentially stealing spin from their neighbors. Over time, this process can accelerate some stars to incredible speeds, while others may slow down. It's a cosmic dance of energy and motion, with each star influencing the others in ways that are still being studied. The effects of such rapid rotation go beyond just altering the stars' shapes. The extreme speeds also impact their internal structures and energy outputs. For instance, the centrifugal force generated by the rapid spin can cause the stars' outer layers to expand, cooling their surfaces and changing their colors. This can make them appear dimmer or even shift their spectral classifications, complicating efforts to study them. Additionally, the intense rotation can generate powerful magnetic fields, leading to frequent and dramatic stellar flares that light up the surrounding space. One of the most fascinating consequences of this rapid spinning is the potential for starquakes, massive tremors that ripple across the surfaces of these stars. These quakes can release enormous amounts of energy, sometimes even altering the star's rotation speeds. Imagine a star so massive and fast spinning that it literally shakes itself, sending shockwaves through its own atmosphere. It's a phenomenon that challenges our understanding of stellar stability and opens up new questions about the limits of stellar physics. As we study HD 67890, we're not just observing a system of fast-spinning stars, we're witnessing the extreme outcomes of gravitational interactions and stellar evolution. These stars, with their distorted shapes and dynamic behaviors, remind us that the universe is full of surprises, constantly pushing the boundaries of what we think is possible. And as we continue our exploration of Undecuple star systems, we'll uncover even more mysteries, like a system where stars exhibit bizarre magnetic fields that defy all expectations. Now, let's shift our gaze to a system where the stars don't just spin fast, they also wield magnetic fields so strange and powerful that they rewrite the rules of stellar behavior. In this Undecuple star system, known as HD 45678, the stars are not only bound by gravity, but also by magnetic forces that create a cosmic spectacle unlike anything we've seen before. These magnetic fields are so intense and unusual that they challenge our understanding of how stars generate and maintain such forces. The stars in HD 45678 possess magnetic fields that are thousands of times stronger than those of typical stars. To give you an idea, Earth's magnetic field, which protects us from harmful solar radiation, is relatively weak compared to the magnetic fields in this system. Here, the star's magnetic fields are so powerful that they can warp the very fabric of space around them, creating ripples in the electromagnetic environment that extend far beyond the stars themselves. These fields are not uniform either. They twist, loop, and even snap, releasing bursts of energy that can be detected across vast distances. But what causes these bizarre magnetic fields? The answer lies in the chaotic interactions within the Undecuple system. With 11 stars orbiting in close proximity, their gravitational and magnetic influences constantly collide. As stars pass near each other, their magnetic fields can become entangled, amplifying their strength and creating complex patterns. Some stars may even steal magnetic energy from their neighbors, leading to wildly fluctuating fields that defy conventional models of stellar magnetism. It's a cosmic tug-of-war, where magnetic forces are as influential as gravity in shaping the system's dynamics. The implications of these unusual magnetic fields are profound, especially when it comes to space weather. In HD 45678, the star's magnetic activity generates intense solar winds and cosmic radiation. These winds are not the gentle streams we associate with our sun. They are violent, high-energy outflows that can strip away atmospheres from nearby planets and disrupt the orbits of smaller objects. The radiation emitted by these stars is equally extreme, posing challenges for any potential life forms in the system and complicating efforts to study the stars up close. One of the most striking effects of these magnetic fields is their ability to create auroras on a cosmic scale. Just as Earth's magnetic field produces the northern and southern lights, the stars in this system can generate auroras that span entire star systems. These auroras are not just beautiful, they are also powerful indicators of the star's magnetic activity, providing astronomers with clues about the internal processes driving these phenomena. Imagine a star so magnetically active that it lights up its entire neighborhood with shimmering, otherworldly displays. As we study HD 45678, we're not just observing a system of stars with unusual magnetic fields, we're uncovering the intricate interplay between magnetism, gravity, and stellar evolution. These stars, with their chaotic magnetic behaviors, remind us that the universe is full of surprises, constantly challenging our understanding of the forces that shape it. And as we continue to explore undecuple star systems, we'll encounter even more mysteries, like a system where stars orbit so closely that they nearly touch, creating a gravitational ballet unlike anything we've ever seen. Now, let's turn our attention to a system where the stars are so close together that they almost seem to dance on the edge of collision. In this undecuple star system, known as KIC 8462857, the stars orbit each other at distances so small that they nearly touch, creating a gravitational spectacle that defies imagination. This system is a cosmic tightrope walk, where the stars are locked in an intricate balance between attraction and destruction. The stars in KIC 8462857 are separated by mere millions of kilometers, a distance that, in cosmic terms, is practically a hair's breadth. To put this into perspective, the closest star to our Sun, Proxima Centauri, is over 4 light-years away. Here, the stars are so close that their outer atmospheres often brush against each other, creating a swirling, chaotic environment. This proximity leads to intense gravitational interactions, where the stars pull and tug at each other, distorting their shapes and creating tidal forces that ripple through their surfaces. But what happens when stars get this close? The gravitational forces at play are immense, and they can lead to some truly extraordinary phenomena. In KIC 8462857, the stars' mutual gravitational pull causes them to stretch and deform, creating elongated shapes that resemble cosmic eggs rather than the spherical forms we typically associate with stars. These tidal distortions also generate immense heat, causing the stars to glow brighter and emit more energy than they would in isolation. One of the most fascinating aspects of this system is the potential for stellar mergers. When stars orbit this closely, there's always the risk that their gravitational dance could spiral out of control, leading to a collision. Such mergers are rare and cataclysmic events, releasing enormous amounts of energy and often resulting in the formation of a single, more massive star. In KIC 8462857, astronomers have observed signs that some of the stars may be on a collision course, hinting at the possibility of a future merger that could reshape the entire system. The gravitational interactions in this system also have profound effects on the surrounding space. The stars' close orbits create ripples in space-time, known as gravitational waves, which propagate outward and can be detected by observatories here on Earth. These waves provide valuable insights into the dynamics of the system, allowing scientists to study the intricate interplay between the stars in unprecedented detail. Additionally, the intense gravitational forces can disrupt the orbits of any planets or smaller objects in the system, making it a challenging environment for the formation of stable planetary systems. Despite the chaos, there's a strange beauty to KIC 8462857. The star's close orbits create a mesmerizing celestial ballet, where the boundaries between individual stars blur and the system becomes a single dynamic entity. It's a reminder of the incredible diversity of star systems in the universe and the endless possibilities for discovery. As we continue to explore Undecuple star systems, we'll encounter even more wonders, like a system where stars follow orbits so irregular that they seem to defy the laws of physics. Now, let's venture into a system where the stars seem to have thrown the rulebook of celestial mechanics out the window. In this Undecuple star system, known as HD 123456, the stars follow orbits so irregular and chaotic that they defy our understanding of how stellar systems should behave. Unlike the predictable, elliptical paths we often see in binary or triple star systems, the stars here move in ways that appear almost random, creating a cosmic puzzle that has left astronomers both baffled and fascinated. The orbits in HD 123456 are anything but ordinary. Instead of following smooth, predictable paths, the stars zigzag through space, sometimes looping around each other in tight spirals before suddenly veering off in entirely new directions. This erratic motion is driven by the complex gravitational interactions between the 11 stars, each pulling and pushing on the others in a constant tug of war. The result is a system where no two orbits are alike, and the stars seem to dance to their own chaotic rhythm. What makes these strange orbits even more intriguing is how they challenge our traditional models of stellar motion. For centuries, astronomers have relied on the laws of gravity to predict how stars and planets move. But in HD 123456, these laws seem to break down, or at least operate in ways we don't fully understand. The system's chaotic orbits suggest that there may be forces at play, perhaps hidden masses, unseen companions, or even exotic physics that we have yet to account for. One theory is that the system's irregular orbits are the result of past close encounters or collisions. If one or more stars in the system were once part of a different star cluster, their gravitational interactions could have thrown the entire system into disarray. Another possibility is that the system is still young and hasn't yet settled into a stable configuration. Over time, the stars may gradually find a more orderly arrangement, but for now, their chaotic dance continues unabated. The implications of these strange orbits extend far beyond HD 123456. By studying this system, astronomers hope to gain new insights into the formation and evolution of complex star systems. It's a reminder that the universe is full of surprises, and even the most well-established theories can be upended by a single, unexpected discovery. As we continue to explore Undecuple star systems, we're likely to encounter even more examples of stellar behavior that push the boundaries of our understanding. But the story doesn't end here. In our next discovery, we'll explore an Undecuple system where the stars emit mysterious signals that have sparked theories about alien technology or natural phenomena. What could these signals mean, and what secrets do they hold? Stay tuned as we unravel another cosmic mystery. Now, let's turn our attention to a discovery that has sparked both curiosity and debate among astronomers. In this Undecuple star system, known as HD 78901, the stars emit mysterious signals that have left scientists scratching their heads. These signals, detected as bursts of radio waves and X-rays, don't match any known natural phenomena, leading to a flurry of theories about their origin, ranging from exotic astrophysical processes to the tantalizing possibility of alien technology. The signals from HD 78901 are unlike anything we've observed before. They come in irregular patterns, sometimes appearing as sharp, sudden bursts and other times as faint, continuous emissions. What's particularly puzzling is that these signals don't align with the typical behavior of stars, even in complex systems. Normally, stars emit radiation in predictable ways, such as the steady glow of thermal energy or the occasional flare caused by magnetic activity. But in this system, the signals seem to defy these norms, appearing almost purposeful in their irregularity. One leading theory is that these signals could be the result of highly energetic events, such as collisions between stars or interactions with unseen objects like neutron stars or black holes. For example, if one of the stars in the system were to pass close to a black hole, the intense gravitational forces could rip apart its outer layers, releasing bursts of energy that we detect as radio or X-ray signals. Alternatively, the signals might be produced by exotic stellar phenomena, such as magnetars neutron stars with incredibly strong magnetic fields, that occasionally release powerful bursts of radiation. However, the mystery deepens when we consider the possibility that these signals might not be natural at all. Some researchers have speculated that they could be evidence of advanced extraterrestrial civilizations. The idea is that an intelligent species might use powerful beams of radio or X-ray energy for communication, propulsion, or even as a way to signal their presence to other civilizations. While this theory is highly speculative, it's not entirely outside the realm of possibility, especially given the sheer number of stars in the universe and the potential for life to arise in unexpected places. To investigate these signals further, astronomers have turned to some of the most advanced telescopes and instruments available. By analyzing the timing, frequency, and intensity of the emissions, they hope to uncover clues about their origin. For instance, if the signals are found to repeat at regular intervals, it could suggest a natural process such as the rotation of a neutron star. On the other hand, if the signals appear to carry encoded information or follow a non-random pattern, it might raise even more intriguing questions about their source. The implications of this discovery are profound, not just for our understanding of Undecuple star systems, but for the broader search for life in the universe. If these signals are indeed natural, they could reveal new types of stellar behavior or exotic astrophysical processes that we've never encountered before. But if they turn out to be artificial, it would be one of the most groundbreaking discoveries in human history, fundamentally altering our place in the cosmos. As we continue to explore the mysteries of HD 78901, one thing is certain: this system has opened up a new frontier in our quest to understand the universe. Whether the signals are the result of natural phenomena or something more extraordinary, they remind us that the cosmos is full of surprises waiting to be uncovered. And with each new discovery, we come one step closer to unraveling the secrets of the stars. But the intrigue doesn't stop here. In our next discovery, we'll delve into an Undecuple system where some stars are nearly invisible, shrouded in mystery due to their low luminosity or unusual composition. What could be hiding in the shadows of these elusive stars? Stay tuned as we uncover another cosmic enigma. Now, shifting our gaze to a system cloaked in cosmic shadows, we encounter an Undecuple star system where some stars are nearly invisible, hidden from view by their faint glow or peculiar makeup. This system, known as KIC 8462852, challenges our ability to observe and understand the full complexity of such stellar arrangements. What makes these stars so elusive, and what secrets do they hold within their dim light? In KIC 8462852, several stars emit so little light that they barely register on even the most sensitive telescopes. These stars, often referred to as dark stars, are not black holes or dead remnants, but rather active stars with extremely low luminosity. Their faintness can be attributed to a combination of factors, such as their small size, cool temperatures, or unusual chemical compositions. For instance, some of these stars might be brown dwarfs, objects that are too massive to be planets, but not massive enough to ignite sustained nuclear fusion, leaving them in a dim, twilight state. The challenge of detecting these stars lies in their contrast with the brighter members of the system. In an undecuple system, the presence of multiple luminous stars can overshadow the faint ones, making them nearly impossible to spot without specialized techniques. Astronomers have turned to methods like gravitational microlensing, where the gravity of a faint star bends the light of a background object, revealing its presence indirectly. Additionally, infrared telescopes have proven invaluable, as these dim stars often emit more heat than visible light, allowing them to be detected in wavelengths invisible to the human eye. One of the most intriguing aspects of these nearly invisible stars is their potential to host planets. While their low luminosity might suggest harsh conditions, some of these stars could still have habitable zones, regions where temperatures are just right for liquid water to exist. Planets orbiting such stars would experience perpetual twilight, with their skies dominated by the faint glow of their host star and the brighter companions in the system. This raises fascinating questions about the potential for life in these shadowy realms and how it might adapt to such unique environments. The unusual composition of these stars also offers clues about their origins. Some may have formed from material that was chemically distinct, leading to their low luminosity. Others might have undergone dramatic changes over time, such as losing much of their outer layers or cooling significantly as they age. By studying these stars, astronomers can piece together the history of the system and gain insights into the diverse pathways of stellar evolution. As we continue to explore KIC 8462852, we're reminded of the vast diversity within undecuple star systems. These nearly invisible stars, though elusive, play a crucial role in shaping the dynamics and mysteries of their cosmic neighborhoods. They challenge our assumptions about what stars can be and push the boundaries of our observational capabilities. But the surprises don't end here. In our next discovery, we'll venture into an undecuple system where stars possess rare atmospheric layers, revealing new dimensions of stellar complexity. What secrets lie within these unusual atmospheres? Stay with us as we uncover yet another layer of the cosmic puzzle. Now, let's turn our attention to a system where the stars themselves wear cloaks of mystery. An undecuple star system where the atmospheres of its stars defy expectations and reveal secrets about the cosmos. In this system, known as HD 123456, astronomers have discovered stars with atmospheric layers so unusual that they challenge our understanding of stellar chemistry and behavior. What makes these atmospheres so extraordinary? Unlike the relatively uniform layers found in most stars, the atmospheres in HD 123456 are layered with rare elements and compounds that create unique spectral signatures. Some stars in this system exhibit atmospheres rich in elements like zirconium, yttrium, and even exotic isotopes that are rarely seen in stellar environments. These elements, often associated with the remnants of ancient supernova, suggest that the stars in this system may have formed from material that was chemically enriched by previous generations of stars. The discovery of these unusual atmospheres was made possible by advanced spectroscopic techniques. By analyzing the light emitted by these stars, astronomers can identify the specific wavelengths absorbed by different elements in their atmospheres. This process, known as spectroscopy, acts like a cosmic fingerprint, revealing the chemical makeup of the stars. In HD 123456, the spectra showed unexpected absorption lines, indicating the presence of these rare elements. This finding not only highlights the diversity of stellar atmospheres, but also provides clues about the history of the system itself. One of the most fascinating aspects of these unusual atmospheres is their impact on the star's behavior. For example, some stars in this system exhibit strange pulsations or irregular brightness changes, likely caused by the unique chemical composition of their outer layers. These pulsations can affect the star's energy output and even influence the orbits of nearby planets or companion stars. In some cases, the rare elements in the atmospheres may also create unusual magnetic fields, adding another layer of complexity to these already enigmatic stars. The presence of such rare elements also raises questions about the origins of the system. Did these stars form in a region of space that was unusually rich in heavy elements? Or did they acquire these materials through interactions with other stars or interstellar clouds? By studying HD 1, 2, 3, 4, 5, 6, astronomers hope to uncover the processes that led to the formation of these chemically unique stars and how they fit into the broader story of galactic evolution. As we explore this system further, we're reminded that even the atmospheres of stars can hold profound secrets. These unusual layers not only challenge our understanding of stellar physics, but also open new avenues for exploring the chemical diversity of the universe. Each discovery in HD 1, 2, 3, 4, 5, 6 brings us closer to unraveling the intricate tapestry of cosmic history. But the mysteries of Undecuple star systems don't stop here. In our next discovery, we'll venture into a system where stars are shrouded in massive dust clouds, creating a cosmic veil that obscures their light and hides their secrets. What lies beneath these dusty shrouds? Stay with us as we continue our journey through the wonders of the cosmos. Now, let's shift our gaze to a system where the stars are cloaked in a cosmic haze. An Undecuple star system where massive dust clouds swirl around its stars, creating a breathtaking yet enigmatic spectacle. This system, known as HD 78901, is home to stars that are almost entirely obscured by thick, swirling clouds of dust. These clouds, composed of tiny particles of silicates, carbon, and other materials, create a veil that dims the star's light and makes them challenging to observe directly. But what causes these dust clouds to form, and what do they tell us about the system's history? The origins of these dust clouds are thought to lie in the remnants of ancient stellar collisions or the debris left behind by dying stars. In HD 78901, astronomers believe that the dust clouds may have formed from the remnants of a catastrophic event, such as the collision of two stars or the explosive death of a massive star. Over time, the debris from these events coalesced into vast clouds that now envelop the surviving stars. These clouds are not static, they are dynamic structures that can shift and change over time, influenced by the gravitational forces of the stars they surround. One of the most striking effects of these dust clouds is their impact on visibility. The dust particles scatter and absorb light, making the stars within the system appear dimmer and redder than they actually are. This phenomenon, known as interstellar extinction, poses a challenge for astronomers trying to study the stars in HD 78901. To overcome this, scientists use infrared and radio telescopes, which can penetrate the dust and reveal the hidden stars beneath. These observations have shown that the stars in this system are far more active and luminous than they appear through the dusty veil. But the dust clouds in HD 78901 are more than just obstacles to observation, they are also sites of potential new beginnings. Within these clouds, particles can clump together, forming the seeds of future planets or even new stars. The dense regions of the clouds may eventually collapse under their own gravity, giving rise to protostars or planetary systems. This means that the dust clouds in this system could be the birthplace of new worlds, adding another layer of intrigue to this already fascinating system. The presence of these massive dust clouds also raises questions about the system's evolution. How did the stars in HD 78901 come to be surrounded by such dense clouds? Were they born in a particularly dusty region of space, or did the clouds form later as a result of stellar activity? By studying the composition and movement of the dust, astronomers hope to piece together the history of this system and understand how it fits into the broader story of galactic formation. As we peer through the dusty veil of HD 78901, we're reminded that even the most obscured corners of the universe hold secrets waiting to be uncovered. These dust clouds, while challenging to study, offer a glimpse into the processes that shape stars and planets, reminding us of the dynamic and ever-changing nature of the cosmos. But our journey through the mysteries of Undecuple star systems continues. Next, we'll explore a system where stars are accompanied by strange and unexpected companions, adding yet another layer of complexity to these cosmic wonders. What kind of companions could these stars have, and how do they influence the system's dynamics? Stay with us as we uncover more of the universe's hidden treasures. Now, let's turn our attention to a system where the stars are not alone. They are accompanied by some of the most unusual companions in the cosmos. In this Undecuple star system, known as HD 123456, the stars share their orbits with objects that defy conventional expectations. Among these companions are neutron stars, brown dwarfs, and other exotic entities that add a layer of complexity and intrigue to this already fascinating system. Neutron stars, the remnants of massive stars that have exploded in supernova, are among the most extreme objects in the universe. In HD 123456, one of the stars is orbited by a neutron star, creating a dynamic and high-energy environment. The gravitational pull of the neutron star is so intense that it distorts the shape of its companion star, pulling material from its outer layers and creating a swirling accretion disk. This process generates powerful X-ray emissions, making this system a hotspot for astronomers studying high-energy astrophysics. But neutron stars aren't the only unusual companions in this system. Brown dwarfs, often referred to as failed stars, also play a significant role. These objects are too massive to be considered planets, but not massive enough to sustain the nuclear fusion that powers true stars. In HD 123456, several brown dwarfs orbit the primary stars, their faint glow barely visible against the backdrop of their brighter companions. These brown dwarfs are thought to have formed alongside the stars, but their exact origins remain a mystery. Some astronomers speculate that they may have been captured by the system's gravitational pull, while others believe they formed in situ from the same cloud of gas and dust. The presence of these unusual companions has profound implications for the system's dynamics. The gravitational interactions between the stars and their companions can lead to chaotic orbits, with some objects being flung out of the system entirely while others are drawn closer together. These interactions also influence the formation and evolution of planets within the system, as the gravitational tugs from neutron stars and brown dwarfs can disrupt the delicate process of planet formation. One of the most intriguing aspects of HD 123456 is the potential for life. While the harsh environment around a neutron star might seem inhospitable, the presence of brown dwarfs raises interesting possibilities. Brown dwarfs can have their own systems of moons, and some of these moons could potentially harbor liquid water and other conditions necessary for life. The idea of life existing in such a system challenges our understanding of habitability and opens up new avenues for exploration. As we study this system, we're reminded that the universe is full of surprises. The unusual companions in HD 123456 not only add to the system's complexity, but also provide valuable insights into the processes that shape star systems. By understanding how these objects interact with their stellar hosts, we can gain a deeper appreciation for the diversity and dynamism of the cosmos. But our exploration of Undecuple star systems doesn't end here. Next, we'll venture into a system where the stars are spread out over vast distances, challenging our notions of gravitational cohesion. How do these stars stay connected, and what does this tell us about the forces that bind the universe together? Stay with us as we continue to unravel the mysteries of these cosmic wonders. Now, let's shift our gaze to a system that defies the very idea of closeness. In this Undecuple star system, known as IC 2147, the stars are scattered across such immense distances that it challenges our understanding of how star systems hold together. Unlike the tightly packed systems we've explored earlier, IC 2147 is a cosmic archipelago with its stars separated by light years of empty space. This vast separation raises fascinating questions about the forces that keep these stars bound to one another. At first glance, it's hard to imagine how such a system could remain intact. Gravitational cohesion, the glue that holds most star systems together, seems almost too weak to maintain order over such enormous distances. Yet IC2147 persists, its stars orbiting a common center of mass despite their extreme separation. This phenomenon suggests that even the faintest gravitational ties can create a delicate balance, binding stars together across the void. One of the most intriguing aspects of this system is how the stars interact, or rather, how they don't. With such vast distances between them, the gravitational influence of each star on its neighbors is minimal. This means that the stars in IC2147 lead largely independent lives, each following its own path around the system's center. For astronomers, this presents a unique opportunity to study stars in isolation, free from the chaotic gravitational tugs that dominate more tightly packed systems. But how did this system come to be? One theory suggests that IC2147 may have formed from an unusually diffuse cloud of gas and dust. As the cloud collapsed, it fragmented into widely spaced clumps, each giving birth to a star. Over time, these stars remained loosely bound, their orbits shaped by the faint gravitational pull of their distant siblings. Another possibility is that the system was once more compact, but over billions of years, gravitational interactions with passing stars or even entire galaxies stretched it out, leaving the stars far apart. The vast distances between the stars also have implications for any planets that might exist in this system. In a typical star system, planets often form within the gravitational sphere of a single star. But in IC2147, the extreme separation of the stars means that any planets would likely orbit just one star, with little influence from the others. This could create isolated planetary systems, each with its own unique conditions and potential for habitability. Studying IC2147 challenges our assumptions about star systems and their formation. It reminds us that the universe is full of surprises, and that even the most basic principles of astrophysics can be stretched to their limits. As we continue to explore Undecuple star systems, we're constantly reminded of the incredible diversity and complexity of the cosmos. But our journey doesn't stop here. Next, we'll explore a system where the stars are packed so tightly together that their gravitational interactions create a chaotic and dynamic environment. How do these stars coexist in such close quarters, and what does this tell us about the forces that shape the universe? Stay with us as we dive deeper into the mysteries of Undecuple star systems. Now, let's turn our attention to a system that stands in stark contrast to the vast expanses of IC2147. In this Undecuple star system, known as HD 3922, the stars are packed so tightly together that their gravitational interactions create a chaotic and dynamic environment. Imagine a cosmic dance floor where the dancers are so close that they're constantly bumping into each other. This is the reality of HD 3922. In this system, the stars orbit each other at distances that are, by astronomical standards, almost uncomfortably close. Some of these stars are separated by just a few million miles, a mere stone's throw in the grand scheme of the universe. This proximity means that the gravitational forces between them are incredibly strong, leading to intense stresses and strains on their structures. The stars in HD 3922 are constantly pulling and tugging at each other, creating a gravitational tug of war that shapes their orbits and behaviors. One of the most striking consequences of this tight packing is the potential for stellar collisions. In most star systems, collisions between stars are rare events occurring only over billions of years. But in HD 3922, the stars are so close that collisions are a real and present danger. When two stars collide, the result is a spectacular explosion of energy, releasing intense bursts of light and radiation. These collisions can also lead to the formation of new, more massive stars or even exotic objects like black holes or neutron stars. But how do these stars manage to coexist in such close quarters without tearing each other apart? The answer lies in the delicate balance of gravitational forces. Each star in the system exerts a pull on its neighbors, creating a complex web of interactions that keeps the system stable, at least for a time. However, this balance is precarious, and even a slight disturbance could send the system spiraling into chaos. For astronomers, HD 3922 offers a unique laboratory to study the limits of gravitational stability and the dynamics of tightly packed star systems. The close proximity of the stars also has implications for any planets that might exist in this system. In such a chaotic environment, planets would face constant gravitational disruptions, making stable orbits nearly impossible. Any planets that do form would likely be ejected from the system or destroyed in the frequent stellar interactions. This makes HD 3922 a fascinating but inhospitable place, where the stars themselves are the main actors in a dramatic cosmic ballet. Studying systems like HD 3922 helps us understand the extremes of stellar dynamics and the forces that shape the universe. It's a reminder that the cosmos is a place of both beauty and violence, where the delicate balance of forces can create both harmony and chaos. As we continue to explore Undecuple star systems, we're constantly reminded of the incredible diversity and complexity of the universe, but our journey doesn't end here. Next, we'll delve into a system where the stars have lifespans that defy our expectations, living much longer or shorter than predicted by current theories. What secrets do these stars hold, and what can they teach us about the life cycles of stars? Stay with us as we uncover more mysteries of Undecuple star systems. Now, let's shift our focus to a system that challenges our understanding of stellar lifespans. In this Undecuple star system, known as Kappa 779, the stars defy the typical timelines predicted by current astronomical models. Some of these stars burn brightly for far longer than expected, while others fade away in what seems like the blink of an eye. This unusual behavior raises fascinating questions about the factors that influence how stars age and evolve. In Kappa 779, one group of stars appears to be living on borrowed time. These stars, which should have exhausted their fuel and faded into stellar remnants, continue to shine with surprising vigor. Astronomers believe this extended lifespan could be due to the unique gravitational interactions within the system. The close proximity of the stars allows them to exchange material, effectively replenishing their fuel supplies and prolonging their lives. It's as if these stars have found a way to cheat death, at least temporarily. On the other hand, some stars in Kappa 779 burn out much faster than expected. These stars, which should have stable lifespans lasting billions of years, instead collapse into stellar remnants in just a fraction of that time. One possible explanation is that these stars are experiencing unusually high rates of mass loss, shedding their outer layers at an accelerated pace. This rapid loss of material could be caused by intense stellar winds or interactions with neighboring stars, stripping them of the fuel they need to sustain their fusion processes. The presence of such contrasting lifespans within a single system is a puzzle that challenges our understanding of stellar evolution. Typically, stars follow predictable life cycles based on their mass and composition. But in Kappa 779, the rules seem to bend, if not break entirely. This anomaly provides astronomers with a unique opportunity to study the factors that can alter a star's lifespan, from gravitational interactions to material exchange and beyond. One intriguing possibility is that the stars in Kappa 779 are influenced by an unseen companion, such as a black hole or a neutron star. The gravitational pull of such an object could disrupt the normal evolution of the stars, causing them to age in unexpected ways. Alternatively, the system's complex dynamics might create conditions that accelerate or delay stellar processes, leading to these unusual lifespans. Studying systems like Kappa 779 not only deepens our understanding of stellar evolution, but also highlights the incredible diversity of the universe. It reminds us that the cosmos is full of surprises, and even the most well-established theories can be challenged by new discoveries. As we continue to explore Undecuple star systems, we're constantly reminded that the universe is far more complex and dynamic than we ever imagined. Next, we'll explore a system where the stars are nearly identical in size, mass, and composition, a rarity that offers its own set of mysteries. What can such uniformity tell us about the formation and evolution of star systems? Stay with us as we uncover more of the universe's secrets. Now, let's turn our attention to a system that stands out for its remarkable uniformity. In this Undecuple star system, known as Epsilon 426, the stars are nearly identical in size, mass, and composition, a cosmic rarity that defies the usual diversity found in most star systems. Imagine a family of stars so similar that they could almost be twins or even clones. This level of uniformity is not just unusual, it's a phenomenon that challenges our understanding of how star systems form and evolve. In Epsilon 426, each star shares an almost identical mass, ranging within a narrow margin of one another. Their compositions, too, are strikingly similar, with nearly the same proportions of hydrogen, helium, and trace elements. Even their sizes are so close that distinguishing one star from another requires precise measurements. This uniformity is incredibly rare, as most star systems exhibit a wide range of stellar types, from massive, luminous giants to smaller, dimmer stars. So, what could explain such an unusual level of similarity? One theory suggests that Epsilon 426 formed from a single, massive cloud of gas and dust that fragmented into nearly identical clumps. Under the right conditions, these clumps could have collapsed into stars with very similar properties. Another possibility is that the stars in this system underwent a process of mutual synchronization, where gravitational interactions and material exchange over billions of years gradually brought them into alignment. This process, while rare, could explain how the stars became so alike. The implications of such uniformity are profound. For one, it raises questions about the conditions required for star formation. If stars can form with such precision, it suggests that the processes governing their birth are far more intricate than we currently understand. Additionally, the nearly identical nature of these stars provides a unique laboratory for studying stellar evolution. By comparing these stars, astronomers can isolate the effects of external factors, such as gravitational interactions or stellar winds, without the complicating influence of differing masses or compositions. Interestingly, the uniformity of Epsilon 426 also has implications for the potential habitability of any planets orbiting these stars. If planets exist in this system, they would likely experience very similar conditions, such as consistent levels of radiation and gravitational stability. This could create an environment where life, if it exists, might develop in parallel across multiple worlds. While no planets have been confirmed in this system yet, the possibility is tantalizing. As we continue to study systems like Epsilon 426, we're reminded of the incredible diversity and complexity of the universe. Even in a system where the stars appear almost identical, there are mysteries waiting to be unraveled. What other secrets might this system hold, and what can it teach us about the formation and evolution of stars across the cosmos? Next, we'll explore a system where the stars exhibit strange pulsation patterns, creating rhythmic changes that defy conventional models of stellar behavior. What causes these unusual pulsations, and what can they tell us about the inner workings of stars? Stay tuned as we dive deeper into the mysteries of Undecuple star systems. Now, let's shift our gaze to a system where the stars themselves seem to dance to an otherworldly rhythm. In this Undecuple star system, known as Kappa 793, the stars exhibit pulsation patterns that are anything but ordinary. These rhythmic changes in brightness and size are not just fascinating to observe, they challenge our understanding of how stars behave and evolve over time. In Kappa 793, the stars pulsate in ways that defy conventional models of stellar behavior. Unlike the predictable pulsations seen in many variable stars, these stars display irregular patterns, with some pulsating rapidly while others fluctuate more slowly. At times, the pulsations even appear to synchronize across multiple stars, creating a cosmic symphony of light and motion. But what causes these unusual pulsations, and what can they tell us about the inner workings of these stars? One possible explanation lies in the complex interplay of gravitational forces within the system. In an undecuple system, the gravitational pull between stars can create tidal forces that distort their shapes and influence their internal dynamics. These distortions can trigger pulsations as the stars expand and contract in response to the changing gravitational environment. Additionally, the transfer of material between stars, known as mass transfer, can also play a role. As stars exchange gas and dust, their internal structures may become unstable, leading to erratic pulsation patterns. Another factor could be the unique composition of these stars. Some stars in Kappa 793 contain higher concentrations of certain elements, such as helium or heavy metals, which can affect how they pulsate. These elements alter the opacity of the star's outer layers, changing how heat and energy are transported within the star. This, in turn, can lead to unusual pulsation behaviors that are not seen in more typical stars. The study of these pulsations provides valuable insights into the life cycles of stars. By analyzing the patterns and frequencies of the pulsations, astronomers can infer details about the star's internal structures, such as their density, temperature, and rotation rates. This information helps us refine our models of stellar evolution and better understand how stars change over time. Moreover, the synchronization of pulsations across multiple stars offers a rare opportunity to study how stars in a complex system interact and influence one another. But the implications of these pulsations go beyond just stellar physics. If planets orbit these pulsating stars, the rhythmic changes in brightness could have profound effects on their environments. For instance, the fluctuating light levels could create extreme temperature variations, potentially making it difficult for life to thrive. On the other hand, the pulsations might also drive atmospheric circulation or even trigger chemical reactions that could support life in unexpected ways. While no planets have been confirmed in Kappa 793 yet, the possibility adds another layer of intrigue to this already fascinating system. As we continue to explore systems like Kappa 793, we're reminded that the universe is full of surprises. Even the seemingly simple act of a star pulsating can reveal profound truths about the cosmos. What other secrets might these rhythmic stars hold, and what can they teach us about the intricate dance of gravity, light, and matter that shapes the universe? Next, we'll venture into a system where stars are surrounded by rings, much like Saturn but on a stellar scale. What could cause such a phenomenon, and what does it reveal about the dynamics of these stars? Stay with us as we uncover more mysteries of undecuple star systems. Now, let's turn our attention to a system where stars are adorned with rings, much like Saturn but on a far grander scale. In this undecuple star system, known as Epsilon 427, the stars are encircled by vast, luminous rings that stretch across millions of kilometers. These stellar rings are not just a stunning visual spectacle, they also hold clues about the formation and evolution of these complex systems. The rings surrounding the stars in Epsilon 427 are composed of dust, gas, and rocky debris, similar to the material found in planetary rings. However, the sheer size and complexity of these stellar rings set them apart. Unlike Saturn's rings, which are relatively flat and confined to a single plane, the rings in this system can extend in multiple directions, creating intricate three-dimensional structures. But how do such massive rings form around stars? One theory suggests that these rings are the remnants of ancient collisions. In an Undecuple system, the gravitational interactions between stars can be chaotic, leading to frequent close encounters or even direct collisions. When two stars collide, the resulting debris can be flung outward, forming a ring of material that orbits the surviving star or stars. Over time, this debris settles into stable orbits, creating the ring systems we observe today. Another possibility is that the rings are formed from material ejected by the stars themselves. As stars age, they can shed their outer layers, releasing gas and dust into space. In a system with multiple stars, this material can be captured and shaped into rings by the complex gravitational forces at play. The composition of these rings also provides valuable insights. Spectroscopic analysis reveals that the rings contain a mix of silicates, metals, and organic compounds, similar to the building blocks of planets. This suggests that the rings could be the birthplaces of new worlds, where dust and gas gradually clump together to form planets or moons. In fact, some astronomers believe that the rings in Epsilon 427 may already be in the early stages of planet formation, with small, dense clumps of material beginning to coalesce. But the presence of rings around stars isn't just about planet formation, it also affects the stars themselves. The rings can act as a buffer, absorbing and redistributing energy from the stars. This can influence the stars' temperatures, luminosities, and even their lifespans. For example, a star surrounded by a dense ring might appear dimmer than expected as the ring blocks some of its light. Conversely, the ring itself can glow brightly, reflecting and re-emitting the star's energy in spectacular displays of light and color. The study of these stellar rings opens up new avenues for understanding the dynamics of Undecuple systems. By examining the structure and composition of the rings, astronomers can piece together the history of the system from its formation to its current state. They can also explore how the rings interact with the stars, influencing their evolution and shaping the environment around them. And of course, the possibility of planet formation within these rings adds another layer of intrigue, raising questions about the potential for life in such exotic settings. As we marvel at the beauty and complexity of Epsilon 427, we're reminded once again of the endless wonders of the cosmos. From pulsating stars to ringed giants, Undecuple systems continue to challenge our understanding and ignite our curiosity. What other secrets might these systems hold, and what can they teach us about the intricate dance of matter, energy, and gravity that shapes the universe? Next, we'll explore a system where stars eclipse each other in bizarre and unpredictable patterns, creating unique light curves that baffle astronomers. What could cause such unusual eclipses, and what do they reveal about the stars involved? Stay tuned as we dive deeper into the mysteries of Undecuple star systems. Now, let's shift our gaze to a system where the stars engage in a cosmic dance of shadows, eclipsing one another in ways that defy conventional patterns. In this Undecuple star system, designated as Kappa 931, the stars orbit so closely and unpredictably that their eclipses create light curves unlike anything astronomers have ever seen. These unusual eclipses are not just a visual oddity, they offer a window into the complex gravitational interactions and orbital mechanics at play in such a densely packed system. In most binary or triple star systems, eclipses follow a predictable rhythm, with stars passing in front of each other at regular intervals. But in Kappa 931, the presence of 11 stars introduces a level of chaos that disrupts these patterns. The gravitational pull of so many stars creates a dynamic environment where orbits are constantly shifting, leading to eclipses that occur at irregular times and with varying intensities. Sometimes one star will pass in front of another, only to be eclipsed itself moments later by a third star. other times, multiple stars may align in such a way that their combined light creates a sudden, dramatic dip in brightness. These erratic eclipses produce light curves graphs that plot the brightness of the system over time, that are full of unexpected peaks and troughs. For astronomers, deciphering these light curves is like trying to solve a puzzle with missing pieces. Each dip in brightness corresponds to an eclipse, but the complexity of the system makes it difficult to determine which stars are involved and how they are interacting. To make matters even more challenging, the eclipses in Kappa 931 often overlap, creating blended signals that require sophisticated modeling to untangle. One of the most intriguing aspects of these unusual eclipses is what they reveal about the stars themselves. By analyzing the light curves, astronomers can infer details about the stars' sizes, shapes, and even their atmospheres. For example, if a star's atmosphere is particularly dense or turbulent, it can distort the light passing through it during an eclipse, leaving a distinct signature in the light curve. In Kappa 931, some of the stars appear to have extended atmospheres or irregular shapes, suggesting that they are being stretched or distorted by the intense gravitational forces in the system. The eclipses also provide clues about the system's history and evolution. The chaotic nature of the eclipses indicates that the star's orbits are not stable and may have been disrupted by past interactions. This could mean that the system has undergone significant changes over time, such as the capture of rogue stars or the collision and merger of existing stars. By studying the timing and patterns of the eclipses, astronomers can piece together a timeline of these events, shedding light on how undecuple systems form and evolve. But the challenges posed by these unusual eclipses are not just scientific, they're also observational. Because the eclipses occur so unpredictably, astronomers must monitor the system continuously to catch them in action. This requires a combination of ground-based telescopes and space observatories, working together to gather data around the clock. Even then, the sheer complexity of the system means that some eclipses may go unnoticed or be misinterpreted, highlighting the need for advanced algorithms and machine learning techniques to analyze the data. As we unravel the mysteries of Kappa 931, we're reminded of the incredible diversity of undecuple star systems. From ringed stars to chaotic eclipses, these systems continue to surprise and challenge us, pushing the boundaries of our understanding. What other secrets might these systems hold, and what can they teach us about the forces that shape the cosmos? Next, we'll explore a system where stars burn at temperatures so extreme that they defy our expectations of stellar behavior. What causes these stars to become so hot or cold, and how do they influence their surroundings? Stay tuned as we continue our journey through the strange and wondrous world of undecuple star systems. Now, let's turn our attention to a system where the stars themselves defy the norms of temperature, burning at extremes that challenge our understanding of stellar behavior. In this undecuple star system, known as Zeta 724, the stars range from scorching infernos to icy cold giants, creating a cosmic environment unlike any other. What causes these stars to reach such extreme temperatures, and how do they influence the dynamics of their system? In most star systems, temperatures tend to fall within a predictable range based on the star's size, age, and composition. But Zeta 724 is anything but ordinary. Here, some stars blaze at temperatures exceeding 100,000 degrees Celsius, while others hover just above absolute zero, barely emitting any heat at all. This stark contrast is not just a curiosity, it's a window into the complex interplay of forces that govern undecuple systems. The scorching stars in Zeta 724 are often the result of intense gravitational interactions. When stars orbit closely, their gravitational pull can compress their cores, driving up temperatures to extreme levels. In some cases, these stars may also be undergoing rapid nuclear fusion, burning through their fuel at an accelerated rate. This process releases enormous amounts of energy, causing the stars to shine with a fierce, almost blinding intensity. The heat from these stars can ionize nearby gas clouds, creating glowing nebulae that light up the surrounding space. On the other end of the spectrum, the frigid stars in this system present an entirely different mystery. These stars are often remnants of older, more massive stars that have exhausted their nuclear fuel and collapsed into dense, cold objects like white dwarfs or neutron stars. Some may even be brown dwarfs, failed stars that never ignited fully and instead radiate minimal heat. The presence of such cold stars in Zeta 724 suggests that the system has undergone significant evolution, with stars dying and cooling over billions of years. The extreme temperatures in this system have profound effects on its overall dynamics. The hot stars emit powerful stellar winds and radiation, which can strip away the atmospheres of nearby planets or even other stars. Meanwhile, the cold stars exert a gravitational influence that can disrupt the orbits of their neighbors, leading to chaotic interactions. In some cases, the temperature differences between stars can create shock waves as hot and cold gases collide, producing bursts of energy that light up the system in unpredictable ways. One of the most fascinating aspects of Zeta 724 is how these temperature extremes affect the potential for life. While the scorching stars make it nearly impossible for planets to retain liquid water or stable atmospheres, the cold stars could provide a refuge for icy worlds or even exotic forms of life adapted to extreme cold. The interplay between these extremes creates a unique environment where the boundaries of habitability are constantly being tested. Studying Zeta 724 also offers insights into the broader processes that shape Undecuple systems. The presence of stars at such extreme temperatures suggests that these systems are highly dynamic, with stars evolving and interacting in ways that are still not fully understood. By analyzing the light and heat emitted by these stars, astronomers can piece together the history of the system, uncovering clues about how it formed and how it might change in the future. As we explore the extremes of Zeta 724, we're reminded of the incredible diversity of the cosmos. From blazing infernos to icy voids, these stars challenge our assumptions and expand our understanding of what's possible in the universe. What other surprises might Undecuple systems hold, and how do these extremes shape the fate of the stars and planets within them? Next, we'll delve into a system where stars contain rare elements and isotopes, offering clues about the origins of the universe itself. What secrets do these unusual chemical signatures hold, and what can they tell us about the building blocks of the cosmos? Stay with us as we continue our journey through the strange and wondrous world of Undecuple star systems. Now, let's shift our gaze to a system where the stars themselves hold secrets written in their very chemistry. In this Undecuple star system, known as Epsilon 937, the stars are not just celestial bodies, they are cosmic laboratories, containing rare elements and isotopes that challenge our understanding of stellar composition and the origins of the universe. What do these unusual chemical signatures reveal, and why are they so significant? Epsilon 937 stands out because its stars are rich in elements that are rarely found in such abundance. These include heavy metals like gold, platinum, and uranium, as well as rare isotopes of lighter elements like carbon and oxygen. The presence of these materials is not just a curiosity, it's a clue to the violent and chaotic processes that shaped the early universe. But how did these elements end up in the stars of Epsilon 937? One theory suggests that these stars formed from the remnants of ancient supernova, the explosive deaths of massive stars. When a supernova occurs, it scatters heavy elements into space, seeding the surrounding gas clouds with the building blocks for new stars and planets. In the case of Epsilon 937, it's possible that multiple supernovae contributed to the formation of its stars, creating a system unusually rich in rare elements. This process, known as nucleosynthesis, is how many of the elements in the periodic table are created. but the abundance in this system is extraordinary. Another possibility is that Epsilon 937 was once part of a larger galaxy that collided with another, triggering a burst of star formation and mixing materials from different regions of space. Such galactic collisions can create environments where rare elements are concentrated, leading to the formation of stars with unique chemical signatures. The stars in this system may have inherited their unusual composition from these ancient cosmic events, preserving a record of the universe's turbulent past. The significance of these chemical signatures goes beyond mere curiosity. By studying the elements in Epsilon 937, astronomers can trace the history of star formation and galaxy evolution. For example, the presence of certain isotopes can reveal the conditions under which the stars formed, such as the temperature and density of the gas clouds. These clues help scientists piece together the timeline of cosmic events, from the birth of the first stars to the formation of complex systems like Epsilon 937. Moreover, the rare elements in this system have practical implications for our understanding of the universe. Elements like gold and platinum are not just valuable on Earth, they are also key to understanding the processes that occur in extreme environments such as neutron star mergers. These events are thought to be the primary source of many heavy elements, and the stars in Epsilon 937 may provide evidence to support this theory. By analyzing the light from these stars, astronomers can detect the fingerprints of these elements, offering insights into the violent processes that created them. The unusual chemical signatures in Epsilon 937 also raise intriguing questions about the potential for life in such systems. While the presence of heavy metals might seem inhospitable, they could also provide the raw materials for complex chemistry, including the formation of planets with unique geological features. Imagine a world with mountains of gold or oceans rich in rare minerals. Such planets could exist in this system, shaped by the extraordinary chemistry of its stars. As we explore Epsilon 937, we're reminded that the universe is not just a collection of stars and planets. It's a vast chemical tapestry woven together by the forces of nature. The rare elements in this system are more than just curiosities. They are windows into the processes that shape the cosmos, from the smallest atoms to the largest galaxies. What other secrets might these stars hold, and how will they deepen our understanding of the universe? Next, we'll journey to a system where stars are surrounded by debris disks, remnants of planetary formation that offer clues about the birth of worlds. What can these dusty rings tell us about the origins of planets, and how do they shape the future of their systems? Stay with us as we continue to unravel the mysteries of Undecuple star systems. Now, let's turn our attention to a system where the stars are cloaked in swirling clouds of cosmic dust and debris. In this Undecuple star system, known as Kappa 724, the stars are not alone. They are surrounded by vast debris disks, remnants of planetary formation that tell a story of creation and destruction. These dusty rings are more than just beautiful cosmic phenomena. They are the birthplaces of planets, offering clues about how worlds come into existence. Debris disks are essentially the leftovers from the formation of a star system. When a star is born, it forms from a collapsing cloud of gas and dust. As the star ignites, the remaining material in the surrounding disk begins to clump together, forming planets, moons, and other celestial bodies. Over time, collisions between these objects break them apart, creating a disk of debris that orbits the star. In Kappa 724, this process has left behind a complex network of debris disks around each of its 11 stars, each one a snapshot of the system's dynamic history. What makes Kappa 724 particularly fascinating is the sheer scale and diversity of its debris disks. Some of the disks are thin and faint, while others are thick and dense, filled with everything from tiny grains of dust to massive chunks of rock and ice. These variations suggest that the system has undergone multiple phases of planetary formation and destruction, with each star carving out its own unique path through the chaos. The presence of so many debris disks in a single system is rare, making Kappa 724 a treasure trove for astronomers studying the origins of planets. One of the key questions surrounding these debris disks is how they influence the potential for planet formation. In some cases, the debris may eventually coalesce into new planets, while in others, it may remain as a chaotic cloud of material, constantly reshaped by gravitational interactions between the stars. The stars in Kappa 724 are so close to one another that their gravitational forces constantly tug at the debris disks, creating intricate patterns and structures. These interactions can either promote or hinder the formation of planets, depending on the balance of forces at play. The debris disks in Kappa 724 also provide valuable insights into the conditions necessary for planet formation. By studying the composition and distribution of the material in these disks, astronomers can determine the types of planets that might form in such a system. For example, a disk rich in heavy metals and silicates could give rise to rocky planets, while one dominated by ice and gas might lead to the formation of gas giants or icy worlds. The diversity of the disks in this system suggests that it could host a wide variety of planets, each with its own unique characteristics. But the story of Kappa 724 doesn't end with planet formation. The debris disks also play a crucial role in shaping the future of the system. Over time, the material in these disks will continue to collide and break apart, creating new generations of planets and moons. Some of the debris may even be ejected from the system entirely, becoming rogue objects drifting through the galaxy. The constant interplay between creation and destruction in Kappa 724 is a reminder of the dynamic nature of the universe, where even the smallest particles can have a profound impact on the evolution of a star system. As we explore Kappa 724, we're reminded that the universe is a place of endless transformation. The debris disks surrounding its stars are not just remnants of the past, they are the seeds of future worlds, waiting to take shape in the cosmic dance of gravity and time. What new planets might emerge from these dusty rings, and how will they shape the destiny of this extraordinary system? Next, we'll venture into a system where stars create strange gravitational lensing effects, bending light in ways that challenge our understanding of space and time. What mysteries lie hidden in these warped regions of the cosmos? Stay with us as we continue to uncover the wonders of Undecuple star systems. Now, let's shift our gaze to a system where the very fabric of space and time seems to twist and warp in extraordinary ways. In this Undecuple star system, known as Epsilon 937, the stars themselves act as cosmic magnifying glasses, bending light in ways that defy our expectations. Gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity, occurs when massive objects like stars warp the space around them, causing light from distant objects to curve as it passes by. But in Epsilon 937, this effect is amplified to an almost surreal degree, creating a celestial spectacle unlike anything we've seen before. What makes this system so unique is the sheer number of stars involved, 11 in total, each contributing to the gravitational lensing effect. As light from distant galaxies or even other stars within the system passes near these massive objects, it doesn't travel in a straight line. Instead, it bends around the stars, creating multiple images, distorted shapes, and even rings of light known as Einstein rings. These visual anomalies are not just fascinating to observe, they provide astronomers with a powerful tool to study the universe. By analyzing how light is bent, scientists can map the distribution of mass within the system, uncovering hidden details about the stars and their surroundings. One of the most striking features of Epsilon 937 is the way its gravitational lensing effects vary over time. Because the stars are in constant motion, orbiting one another in a complex dance, the way they bend light changes as their positions shift. This creates a dynamic, ever-changing view of the system, where distant objects might appear to flicker, stretch, or even multiply as the stars move. It's like looking through a kaleidoscope made of gravity, where the patterns are never the same twice. But the implications of this gravitational lensing go far beyond just creating beautiful cosmic visuals. These effects allow astronomers to peer deeper into the universe than ever before. By using the stars in Epsilon 937 as natural telescopes, scientists can observe objects that would otherwise be too faint or distant to see. This includes everything from ancient galaxies at the edge of the observable universe to rogue planets drifting through the void. The system acts as a window into the cosmos, revealing secrets that would remain hidden without the help of its gravitational lensing. Another intriguing aspect of Epsilon 937 is how its lensing effects challenge our understanding of gravity itself. While Einstein's theory of general relativity has been incredibly successful in explaining gravitational lensing, systems like this one push the boundaries of what we know. The complex interactions between 11 stars create scenarios where the rules of gravity seem to bend in unexpected ways. Studying these anomalies could lead to new insights into the nature of gravity, potentially uncovering flaws or limitations in our current theories. The gravitational lensing in Epsilon 937 also has practical applications for the search for exoplanets. When a planet passes in front of a star, it can cause a temporary brightening of the star's light, a phenomenon known as microlensing. In a system with so many stars, the chances of detecting these events increase dramatically. This makes Epsilon 937 a prime location for discovering new worlds, some of which might be hidden in the outer reaches of the system or even orbiting other stars entirely. As we explore the strange and mesmerizing effects of gravitational lensing in Epsilon 937, we're reminded of the profound interconnectedness of the universe. The way light bends and twists around these stars is a testament to the power of gravity, shaping not just the stars themselves but the very fabric of reality. What other mysteries might this system reveal as we continue to study its warped and wondrous light? Next, we'll journey to a system where stars are part of a larger cluster, their fates intertwined in a cosmic web of gravity and motion. How do these stars influence one another, and what secrets do they hold about the evolution of star systems? Stay with us as we delve deeper into the mysteries of Undecuple star systems. Now, let's venture into a cosmic neighborhood where stars don't just exist in isolation, but are part of a bustling stellar community. Imagine an Undecuple star system not floating alone in the void but embedded within a massive star cluster, a dense gathering of hundreds or even thousands of stars all bound together by gravity. This system, known as IC4891, offers a fascinating glimpse into how stars interact when they're part of a larger family. In IC4891, the 11 stars of the Undecuple system are surrounded by a sea of other stars, each exerting its own gravitational pull. This creates a dynamic environment where the stars are constantly influencing one another, their orbits shaped not just by their immediate companions but by the entire cluster. The gravitational forces at play here are immense, leading to complex and often chaotic interactions. Stars in this system don't just orbit each other, they're also tugged and pulled by the surrounding cluster, creating a cosmic dance that's as intricate as it is mesmerizing. One of the most striking aspects of this system is how the cluster's gravity affects the stability of the Undecuple stars. In a typical star system, the gravitational interactions are relatively predictable, with stars following stable orbits around a common center of mass. But in IC4891, the presence of so many nearby stars introduces a level of unpredictability. The orbits of the Undecuple stars can shift dramatically over time, sometimes leading to close encounters or even collisions. This constant gravitational tug-of-war makes the system a living laboratory for studying how stars behave in crowded environments. The cluster also plays a crucial role in the evolution of the Undecuple system. Over millions of years, the gravitational interactions within the cluster can strip away some of the stars from the Undecuple system, or even add new ones. This process, known as stellar exchange, can fundamentally alter the composition and structure of the system. Imagine a star from the cluster being pulled into the Undecuple system, or one of the original 11 stars being ejected into the cluster. These events are rare but can have profound effects, reshaping the system in ways that challenge our understanding of star formation and evolution. Another fascinating feature of IC 4891 is how the cluster's environment influences the stars themselves. In such a densely packed region, stars are more likely to interact with one another, exchanging material or even merging. This can lead to the formation of exotic objects, such as blue straggler stars that appear younger and more massive than their neighbors due to collisions or mass transfer. The Undecuple system within IC 4891 is no exception, with some of its stars showing signs of past interactions that have left them with unusual properties. The cluster also provides a unique backdrop for studying the Undecuple system. Because the stars in the cluster are all roughly the same age and formed from the same cloud of gas and dust, they offer valuable insights into the conditions that gave rise to the Undecuple system. By comparing the stars in the Undecuple system to those in the surrounding cluster, astronomers can piece together the history of how these systems form and evolve. It's like having a time capsule that preserves the early stages of star formation, allowing us to study the processes that shape the universe. As we explore the Undecuple system within IC 4891, we're reminded of the interconnectedness of the cosmos. The stars in this system are not isolated entities but part of a larger web of gravity and motion, their fates intertwined with those of their neighbors. What other secrets might this system reveal as we continue to study its place within the cluster? And how might these insights help us understand the broader story of star formation and evolution in the universe? Next, we'll turn our attention to a system where stars form unusual binary pairs, their orbits and interactions defying traditional models of stellar motion. What makes these pairs so unique, and what can they teach us about the diversity of star systems? Stay with us as we uncover more mysteries of Undecuple star systems. Now, let's shift our gaze to a system where the stars themselves defy expectations, forming pairs that challenge everything we thought we knew about binary systems. In this Undecuple star system, some of the stars don't just orbit each other in predictable ways. They form unusual binary pairs with orbits and interactions that leave astronomers scratching their heads. These aren't your typical twin stars circling each other in a neat, stable dance. Instead, they're locked in chaotic, irregular orbits that seem to break the rules of stellar motion. One of the most striking examples in this system is a pair of stars that orbit each other in a highly elliptical path. Unlike the smooth, circular orbits we often see in binary systems, these two stars swing wildly close to each other before hurtling far apart, only to be pulled back together by gravity. This extreme variation in distance creates intense gravitational forces, causing the stars to stretch and distort as they move. At their closest approach, the stars are so near that they almost touch, exchanging material and creating a swirling cloud of gas and dust around them. This constant push and pull not only shapes their orbits but also influences their evolution, leading to unusual changes in brightness and temperature. Another fascinating binary pair in this system consists of stars with vastly different masses. One star is a massive, luminous giant, while its companion is a small, dim dwarf. Despite their size difference, the two stars are locked in a tight orbit, with the smaller star whipping around its larger partner at incredible speeds. This imbalance creates a gravitational tug-of-war, where the larger star's gravity pulls material from the smaller one, forming a glowing accretion disk around the giant. Over time, this process can dramatically alter both stars, with the smaller star losing mass and the larger one growing even more massive. It's a cosmic partnership that's as destructive as it is mesmerizing. What makes these binary pairs truly unusual, though, is their ability to influence the entire Undecuple system. The gravitational interactions between these pairs and the other stars in the system create a ripple effect, destabilizing orbits and triggering unpredictable events. For example, a close encounter between one of these binary pairs and a single star could fling the star out of the system entirely or send it spiraling into another star, leading to a collision. These chaotic interactions make the system a dynamic and ever-changing environment, offering astronomers a unique opportunity to study the effects of extreme gravitational forces. But the surprises don't end there. Some of these binary pairs also exhibit strange behaviors, such as sudden bursts of energy or erratic changes in their magnetic fields. These phenomena are thought to be caused by the intense gravitational and magnetic interactions between the stars, which can generate powerful flares or even trigger explosive events. In one particularly dramatic case, a binary pair in this system was observed emitting a series of bright X-ray flares, each one more intense than the last. These flares are believed to be the result of magnetic reconnection, a process where the star's magnetic fields snap and release enormous amounts of energy. It's a reminder that even in the vastness of space, the interactions between stars can be as violent as they are beautiful. As we study these unusual binary pairs, we're reminded of the incredible diversity of star systems in the universe. These pairs challenge our understanding of how stars form and evolve, showing us that even the most basic rules of stellar motion can be bent or broken under the right conditions. What other secrets might these binary pairs hold, and how might their interactions shape the future of the Undecuple system they call home? Next, we'll explore a system where stars are accompanied by exotic moons, each with its own unique characteristics. What makes these moons so unusual, and what can they tell us about the environments around distant stars? Stay with us as we continue our journey through the mysteries of Undecuple star systems. Now, let's turn our attention to a system where the stars are not the only celestial bodies stealing the show. In this Undecuple star system, the stars are accompanied by exotic moons, each with its own set of bizarre and fascinating characteristics. These moons are far from the quiet, barren worlds we often imagine. They are dynamic, active, and full of surprises. One of the most striking moons in this system is a volcanic powerhouse. Unlike the dormant moons we're familiar with, this one is constantly erupting, spewing lava and ash into space. Its surface is a patchwork of glowing rivers of molten rock and towering volcanic peaks, creating a landscape that looks more like a scene from a science fiction movie than a real celestial body. The intense heat from these eruptions has even created a thin, temporary atmosphere around the moon, which glows faintly in the light of its parent star. Scientists believe that the moon's volcanic activity is driven by the gravitational forces exerted by the nearby stars, which stretch and squeeze the moon's interior, generating enough heat to melt rock. Another moon in this system is a frozen wonderland covered in thick layers of ice. But this isn't just any ice, it's a complex mixture of water, methane, and other volatile compounds that create a surface that's both beautiful and treacherous. The ice is constantly shifting and cracking, forming towering ridges and deep crevices. Beneath the icy crust, there's evidence of a subsurface ocean, kept liquid by the gravitational forces of the stars. This hidden ocean could potentially harbor life, making this moon a prime target for future exploration. The interplay between the icy surface and the liquid ocean below creates a dynamic environment that's unlike anything we've seen in our own solar system. Yet another moon in this system is a rocky world with a twist. It's covered in a thick layer of metallic dust. This dust is thought to be the remnants of ancient meteorite impacts, which have pulverized the moon's surface over billions of years. The metallic dust gives the moon a unique, shimmering appearance, reflecting the light of the stars in dazzling patterns. But the dust isn't just for show, it also plays a crucial role in the moon's environment. The dust particles are highly conductive, creating a natural electrical field that interacts with the star's magnetic fields. This interaction generates powerful auroras that light up the moon's sky in a spectacular display of colors. What makes these moons truly remarkable is their ability to influence the stars they orbit. The gravitational pull of the moons can cause subtle changes in the stars' orbits, creating a complex dance of celestial bodies. In some cases, the moon's gravitational forces can even trigger stellar flares or other energetic events. This mutual influence between the stars and their moons adds another layer of complexity to the system, making it a fascinating subject for astronomers. As we study these exotic moons, we're reminded of the incredible diversity of celestial bodies in the universe. Each moon has its own unique story to tell, offering us a glimpse into the many ways that planets and moons can evolve. What other secrets might these moons hold, and how might their interactions with the stars shape the future of this undecuple system? Next, we'll explore a system where stars emit powerful solar winds, creating a turbulent environment that challenges our understanding of stellar behavior. What drives these winds, and what effects do they have on the surrounding space? Stay with us as we continue our journey through the mysteries of undecuple star systems. Now, let's shift our gaze to a system where the stars themselves are the source of some truly extraordinary phenomena. In this undecuple star system, the stars don't just shine. They unleash powerful and erratic solar winds that ripple through the surrounding space, creating a turbulent and dynamic environment. These solar winds are far from the steady streams we observe in our own solar system. Instead, they are unpredictable, intense, and capable of reshaping the very fabric of the system. The solar winds in this system are driven by the star's extreme magnetic activity. Unlike the relatively calm magnetic fields of stars like our Sun, these stars have magnetic fields that are chaotic and highly unstable. This instability causes the stars to release bursts of charged particles at incredible speeds, sometimes reaching velocities hundreds of times faster than the solar winds we're familiar with. These winds carry with them immense amounts of energy, which can have dramatic effects on anything in their path. One of the most striking consequences of these solar winds is their impact on the system's planets and moons. The constant bombardment of charged particles strips away atmospheres, erodes surfaces, and even alters the orbits of smaller bodies. In some cases, the winds are so intense that they carve out vast cavities in the surrounding space, creating regions of low density that stand out against the denser interstellar medium. These cavities act like cosmic vacuums, pulling in nearby material and triggering the formation of new structures, such as shock waves and magnetic bubbles. But the effects of these solar winds aren't limited to the physical environment. They also play a crucial role in shaping the system's electromagnetic landscape. The charged particles carried by the winds interact with the star's magnetic fields, generating powerful electromagnetic waves that ripple through the system. These waves can disrupt communication between spacecraft, interfere with observational instruments, and even pose risks to any potential future missions to the system. For astronomers, studying these waves provides valuable insights into the complex interplay between magnetic fields and charged particles in extreme environments. Perhaps the most fascinating aspect of these solar winds is their unpredictability. Unlike the steady, predictable winds of our Sun, the winds in this system can change direction and intensity without warning. This erratic behavior is thought to be caused by the stars' close proximity to one another, which creates a gravitational tug of war that destabilizes their magnetic fields. As a result, the system is in a constant state of flux, with solar winds that can shift from a gentle breeze to a raging storm in a matter of hours. The study of these unusual solar winds challenges our understanding of stellar behavior and the forces that shape star systems. It raises questions about how such extreme conditions arise and what they mean for the long-term evolution of the system. Could these winds eventually strip away the star's outer layers, altering their structure and lifespan? Or might they trigger new cycles of star formation as the winds compress nearby gas clouds? As we continue to explore this system, we're reminded of the incredible diversity of stellar phenomena and the many ways in which stars can influence their surroundings. Next, we'll venture into a system caught in the midst of a galactic collision where chaos and transformation reign supreme. What happens when entire galaxies collide, and how does it affect the stars within? Stay with us as we uncover the next chapter in the mysteries of Undecuple star systems. Now, let's journey into a cosmic battlefield where stars are caught in the throes of a galactic collision. Imagine two massive galaxies, each containing billions of stars, hurtling toward each other at unimaginable speeds. In the heart of this chaos lies an Undecuple star system, a complex web of 11 stars that finds itself at the center of this celestial clash. The forces at play here are beyond anything we've encountered before, and the effects on this system are nothing short of extraordinary. When galaxies collide, it's not just a simple crash, it's a slow, intricate dance of gravity and momentum that unfolds over millions of years. The stars within these galaxies, including those in our Undecuple system, are pulled and pushed by the immense gravitational forces at work. Some stars are flung out into the void, while others are drawn closer together, creating new and unexpected configurations. In this system, the 11 stars are subjected to extreme gravitational stresses, causing their orbits to warp and shift in ways that defy conventional models of stellar motion. One of the most dramatic consequences of this collision is the intense burst of star formation it triggers. As the galaxies merge, vast clouds of gas and dust are compressed, igniting the birth of new stars. In our Undecuple system, this process has led to the creation of several young, hot stars that burn brightly alongside their older counterparts. These new stars add another layer of complexity to the system, as their intense radiation and stellar winds interact with the existing stars, creating a dynamic and ever-changing environment. But the chaos doesn't stop there. The collision also generates powerful shock waves that ripple through the system, heating the surrounding gas to millions of degrees and producing brilliant bursts of X-ray radiation. These shock waves can disrupt the delicate balance of the system, causing stars to collide or merge and even triggering the formation of black holes. In some cases, the gravitational interactions between the stars become so intense that they form tight binary or even trinary pairs, further complicating the system's structure. For the planets and other bodies within this system, the effects are equally dramatic. The constant bombardment of radiation and gravitational disturbances can strip away atmospheres, destabilize orbits, and even shatter smaller bodies. Any potential for habitability is quickly erased as the system becomes a turbulent and hostile environment. Yet, amidst this chaos, there is also beauty. The collision creates stunning visual displays with streams of stars and gas stretching across the sky, illuminated by the light of countless newborn stars. Studying this Undecuple system offers astronomers a rare glimpse into the transformative power of galactic collisions. It challenges our understanding of how star systems form and evolve under extreme conditions, and it raises intriguing questions about the fate of such systems in the long term. Will the stars eventually settle into new, stable orbits, or will the system continue to be reshaped by the ongoing collision? As we continue to observe this cosmic spectacle, we're reminded of the incredible forces that shape our universe and the endless possibilities they create. Next, we'll explore a system where stars experience intense magnetic storms, revealing yet another layer of the mysteries that Undecuple star systems hold. What happens when stars unleash their magnetic fury, and how does it affect the space around them? Stay tuned as we dive deeper into the wonders of these cosmic enigmas. Now, let's turn our attention to a system where the stars themselves seem to have a fiery temper. In this Undecuple star system, the stars are not just burning steadily, they're erupting with massive and frequent flares, creating a cosmic spectacle that's as dangerous as it is mesmerizing. These flares are not your average solar outbursts. They are colossal eruptions of energy, releasing radiation and charged particles that can wreak havoc on anything in their path. The stars in this system are particularly active, with some flaring up multiple times a day. These flares are caused by the sudden release of magnetic energy stored in the star's atmospheres. When the magnetic fields become twisted and unstable, they snap, unleashing bursts of energy that can outshine the stars themselves for brief moments. The sheer scale of these flares is staggering. Some are thousands of times more powerful than anything our own sun has ever produced. For astronomers, observing this system is both a thrill and a challenge. The unpredictability of the flares makes it difficult to study the stars in detail. Just as one flare subsides, another can erupt, overwhelming telescopes with intense light and radiation. This constant activity also poses risks to any nearby planets or spacecraft. The high-energy particles and radiation from the flares can strip away atmospheres, damage electronics, and even pose a threat to any potential life forms. One of the most intriguing aspects of this system is how the flares interact with the other stars. In an Undecuple system, the stars are so closely packed that the effects of one flare can ripple through the entire system. A massive flare from one star can trigger magnetic disturbances in its neighbors, leading to a chain reaction of activity. This interconnectedness creates a dynamic and chaotic environment where the stars are constantly influencing each other in unpredictable ways. Despite the challenges, studying this system provides valuable insights into the behavior of active stars. It helps scientists understand the mechanisms behind stellar flares and how they impact their surroundings. This knowledge is crucial for predicting space weather and protecting future missions to other star systems. It also raises fascinating questions about the limits of habitability in such extreme environments. Could any planet survive the relentless bombardment of flares, or would life need to adapt in ways we can't yet imagine? As we continue to explore this fiery Undecuple system, we're reminded of the raw power of the universe and the delicate balance that governs even the most chaotic environments. Next, we'll venture into a system where stars are surrounded by glowing nebulae, painting the cosmos with breathtaking beauty. What secrets do these cosmic clouds hold, and how do they shape the stars within them? Stay with us as we uncover more wonders of the universe. Now, let's step into a realm where the stars are not just points of light, but are cloaked in ethereal clouds of glowing gas and dust. In this Undecuple star system, the stars are surrounded by vast, luminous nebulae, creating a celestial canvas that is as stunning as it is mysterious. These nebulae are not just passive backdrops, they are dynamic regions of star formation, where the raw materials of the universe come together to birth new stars and shape the cosmos. The origins of these nebulae are tied to the life cycles of the stars themselves. As stars age, they shed their outer layers, releasing gas and dust into space. In this system, the close proximity of the stars means that their expelled material often collides and mingles, forming intricate structures that glow with vibrant colors. The intense radiation from the stars ionizes the gas, causing it to emit light in hues of red, blue, and green. This interplay of light and matter creates a visual spectacle that has captivated astronomers and stargazers alike. One of the most fascinating aspects of these nebulae is their role in the system's evolution. The gas and dust within them can collapse under gravity, giving rise to new stars. In this Undecuple system, the process is amplified by the sheer number of stars, creating a fertile environment for star formation. The nebulae act as cosmic nurseries where the next generation of stars begins its journey. This constant cycle of creation and destruction ensures that the system remains vibrant and ever-changing. The beauty of these nebulae is not just skin deep. Their intricate structures reveal clues about the forces at work within the system. Shock waves from stellar winds and supernova carve out cavities and filaments, while magnetic fields shape the gas into swirling patterns. These features provide a window into the complex interactions between the stars and their surroundings, offering insights into the physics of star formation and the dynamics of multi-star systems. For astronomers, studying these nebulae is like piecing together a cosmic puzzle. By analyzing the light emitted by the gas, they can determine its composition, temperature, and motion. This information helps them understand how the nebulae formed and how they influence the stars within them. It also raises intriguing questions about the potential for planets to form in such environments. Could these glowing clouds harbor the seeds of new worlds, or are they too chaotic for stable planetary systems to emerge? As we marvel at the beauty of this Undecuple system, we're reminded of the interconnectedness of the universe. The stars and nebulae are not isolated entities but part of a grand tapestry, woven together by gravity and light. Next, we'll explore a system where stars exert extreme tidal forces on each other, creating distortions that defy our expectations. What happens when stars get too close, and how do these forces shape their destinies? Stay with us as we continue our journey through the wonders of the cosmos. Now, let's turn our attention to a system where the stars are locked in a gravitational dance so intense that it warps their very shapes. In this Undecuple star system, the stars exert extreme tidal forces on one another, creating distortions that challenge our understanding of stellar behavior. These tidal forces arise when the gravitational pull of one star stretches and compresses another, much like the way the moon tugs at Earth's oceans but on a cosmic scale. The effects of these tidal forces are nothing short of dramatic. As the stars orbit each other at close distances, their gravitational interactions cause them to bulge and deform. Some stars are stretched into elongated shapes, resembling cosmic eggs rather than perfect spheres. Others develop swirling patterns on their surfaces as the tidal forces churn their outer layers. These distortions are not just visual curiosities, they have profound implications for the star's evolution and stability. One of the most striking consequences of these tidal forces is the transfer of material between stars. As one star stretches toward its companion, it can lose some of its outer layers, which are then pulled into the other star. This process, known as mass transfer, can dramatically alter the star's compositions and lifespans. In some cases, it can even trigger explosive events such as nova or supernova, as the transferred material ignites on the surface of the receiving star. The tidal forces also generate immense heat within the stars. The constant stretching and compressing create friction, which heats the star's interiors to extreme temperatures. This heat can drive powerful stellar winds, ejecting material into space and shaping the surrounding environment. In this Undecuple system, the combined effects of multiple stars exerting tidal forces on each other create a chaotic and dynamic environment where the stars are in a constant state of flux. For astronomers, studying these tidal interactions provides valuable insights into the physics of multi-star systems. By observing the distortions and movements of the stars, they can measure the strength of the tidal forces and understand how they influence stellar evolution. These observations also raise intriguing questions about the potential for planets to exist in such systems. Could planets survive the intense gravitational tugs of these stars, or would they be torn apart or flung into space? As we explore this Undecuple system, we're reminded of the delicate balance that governs the cosmos. The stars' interactions are a testament to the power of gravity, shaping not only their own destinies but also the fate of any worlds that might orbit them. Next, we'll venture into a system where stars are part of a stellar stream, drifting through the galaxy like cosmic nomads. What secrets do these wandering stars hold, and how do they shape the galaxy around them? Stay with us as we continue our journey through the wonders of the universe. Now, let's shift our gaze to a truly mesmerizing Undecuple star system that is part of a stellar stream, a cosmic river of stars flowing through the galaxy. Unlike most star systems that remain anchored in their galactic neighborhoods, this Undecuple system is on the move, drifting through space as part of a larger stellar current. But how did these stars become part of such a stream, and what does their journey tell us about the galaxy's history? Stellar streams are long, ribbon-like structures made up of stars that were once part of a smaller galaxy or star cluster. Over time, the immense gravitational pull of a larger galaxy, like our Milky Way, can tear these smaller systems apart, scattering their stars into elongated trails. In the case of this Undecuple system, the stars were likely once part of a dense cluster that was disrupted by the Milky Way's gravity. As the cluster was pulled apart, its stars were stretched into a stream, with this Undecuple system now embedded within it. What makes this system particularly fascinating is how its stars interact with the stream itself. As they move through the galaxy, the stars are influenced not only by their mutual gravitational bonds, but also by the gravitational forces of the stream and the Milky Way. This creates a delicate balancing act where the stars must navigate the competing pulls of their companions and the larger galactic environment. The result is a system that is both tightly bound and dynamically influenced by its surroundings. The movement of this Undecuple system through the stellar stream also provides a unique opportunity for astronomers to study the history of the galaxy. By tracing the path of the stream and analyzing the motion of its stars, scientists can piece together the events that led to its formation. This includes understanding how the original cluster was disrupted, how long ago it happened, and even the distribution of dark matter in the galaxy, which plays a crucial role in shaping stellar streams. One of the most intriguing aspects of this system is the possibility that it could host planets. While the chaotic environment of a stellar stream might seem inhospitable, the gravitational stability of the Undecuple system itself could provide a safe haven for planets to form and survive. If such planets exist, they would offer a rare glimpse into how planetary systems evolve in such dynamic and ever-changing environments. As we follow the journey of this Undecuple system through the stellar stream, we're reminded of the interconnectedness of the cosmos. The star's movement is not just a random drift, but a story written in the fabric of the galaxy, shaped by forces both seen and unseen. Next, we'll explore an Undecuple system where stars emit powerful jets of material, carving out their own paths through the void of space. What drives these cosmic jets, and what impact do they have on their surroundings? Stay with us as we continue to unravel the mysteries of the universe. Now, let's turn our attention to an Undecuple star system that defies everything we thought we knew about how planets form and orbit. In this system, the planets don't follow the neat, predictable paths we're used to seeing in our own solar system. Instead, they move in strange, almost chaotic patterns, orbiting multiple stars in ways that challenge our understanding of planetary formation. Imagine a planet that doesn't just orbit one star, but dances around 2, 3, or even more stars in a complex gravitational ballet. In this Undecuple system, planets are locked in orbits that crisscross between the stars, creating a dynamic and ever-changing environment. These bizarre configurations raise questions about how such planets could have formed in the first place. Traditional models of planetary formation suggest that planets coalesce from a disk of gas and dust around a single star. But in this system, the presence of multiple stars complicates the process, forcing us to rethink the rules. One of the most striking features of this system is the way the planet's orbits are influenced by the gravitational tug of war between the stars. As the stars move in their own intricate orbits, they pull the planets along, creating paths that are anything but stable. Some planets may even switch their primary star over time, moving from one gravitational influence to another. This constant shifting makes it nearly impossible for these planets to settle into the kind of stable, circular orbits we see in systems like our own. The unusual orbits of these planets also have significant implications for their potential habitability. In a system where a planet's distance from its star or stars can vary dramatically, the conditions on its surface could change drastically over time. A planet might experience periods of intense heat followed by extreme cold, making it difficult for life as we know it to survive. Yet, the very existence of these planets challenges us to consider the possibility of life in environments we once thought were too chaotic to support it. Astronomers are particularly fascinated by how these planets could have formed in such a turbulent environment. One theory suggests that the planets may have originated in the outer regions of the system, where the gravitational influence of the stars was weaker. Over time, they could have migrated inward, getting caught in the complex web of gravitational forces that now defines their orbits. Another possibility is that the planets formed much closer to the stars, but their orbits were disrupted by the stars' interactions, sending them on wild, unpredictable paths. This Undecuple system serves as a reminder that the universe is far more diverse and unpredictable than we often assume. It challenges us to expand our understanding of planetary systems and consider the countless ways they can form and evolve. As we continue to explore the cosmos, systems like this one push the boundaries of what we thought was possible, opening up new questions and possibilities for discovery. Next, we'll dive into an Undecuple system where dark matter plays a surprising role, shaping the stars and their surroundings in ways that are both mysterious and profound. What secrets does dark matter hold, and how does it influence the behavior of these stars? Stay with us as we uncover more cosmic mysteries. Now, let's shift our focus to an Undecuple star system where the invisible hand of dark matter shapes the very fabric of its existence. In this system, dark matter isn't just a passive observer. It's an active participant, influencing the stars and their surroundings in ways that are both mysterious and profound. Dark matter, which makes up about 85% of the universe's mass, is notoriously difficult to detect because it doesn't emit, absorb, or reflect light. Yet, in this Undecuple system, its presence is unmistakable, leaving behind clues that astronomers have pieced together to reveal its hidden influence. One of the most striking ways dark matter manifests in this system is through its gravitational effects. While the stars themselves are bound by their own gravitational interactions, dark matter adds an extra layer of complexity. It forms a vast, invisible halo around the system, exerting a gravitational pull that subtly alters the star's movements. This dark matter halo acts like an unseen scaffold, holding the system together and shaping the paths of the stars in ways that would otherwise be impossible to explain. Without dark matter, the stars in this Undecuple system might drift apart, unable to maintain their intricate dance. But how do astronomers detect something they can't see? The answer lies in the stars themselves. By carefully observing the stars' motions, scientists have noticed subtle anomalies, tiny deviations from the expected paths. These deviations can't be explained by the visible matter alone, pointing to the presence of dark matter. Additionally, gravitational lensing, a phenomenon where light from distant objects is bent by the gravitational field of massive objects, has provided further evidence. In this system, the dark matter halo bends the light from background stars and galaxies, creating distortions that reveal its hidden mass. The effects of dark matter in this system go beyond just influencing the star's orbits. It also plays a role in the system's overall stability. Dark matter's gravitational pull helps to counteract the chaotic forces that would otherwise tear the system apart. In a way, it acts as a cosmic glue, holding the stars together and allowing them to coexist in such a complex arrangement. This stabilizing effect is particularly important in an Undecuple system, where the gravitational interactions between multiple stars could easily lead to instability. Another fascinating aspect of this system is how dark matter interacts with the star's environments. While dark matter doesn't directly interact with light or other forms of electromagnetic radiation, it can influence the distribution of gas and dust within the system. This, in turn, affects the formation of new stars and planets. In some cases, dark matter's gravitational pull can even trigger the collapse of gas clouds, leading to the birth of new stars. This means that dark matter isn't just a passive backdrop, it's an active player in the system's evolution. The presence of dark matter in this Undecuple system also raises intriguing questions about the nature of the universe itself. Why does dark matter seem to cluster around certain systems while remaining sparse in others? What role does it play in the formation and evolution of complex star systems like this one? These are questions that astronomers are still working to answer, and systems like this one provide valuable clues. As we continue to explore the cosmos, Undecuple systems like this one remind us that there's still so much we don't understand. Dark matter, though invisible, is a fundamental part of the universe, shaping the stars and systems we observe in ways we're only beginning to comprehend. Its presence in this system challenges us to rethink our understanding of gravity, star formation, and the very structure of the universe. Next, we'll explore an Undecuple system where stars emit radiation in strange and unexpected patterns, revealing yet another layer of cosmic mystery. What causes these unusual emissions, and what do they tell us about the stars themselves? Stay with us as we uncover more secrets of the universe. Now, let's turn our attention to an Undecuple star system where the stars themselves seem to defy the norms of cosmic behavior, emitting radiation in patterns that baffle even the most seasoned astronomers. This system, with its 11 stars, doesn't just shine, it radiates in ways that challenge our understanding of stellar physics. The unusual radiation patterns observed here aren't just random anomalies, they're clues to deeper mysteries lurking within these stars. At the heart of this system lies a star that emits bursts of radiation at irregular intervals, unlike the steady glow we typically associate with stars. These bursts are intense and unpredictable, sometimes lasting for hours and other times vanishing in mere seconds. What's even more puzzling is that these bursts don't follow any discernible pattern, making them difficult to predict or study. Astronomers have theorized that this erratic behavior could be linked to the star's internal dynamics, such as unstable magnetic fields or turbulent plasma flows deep within its core. But this star isn't alone in its peculiar behavior. Another star in the system emits radiation in a completely different way. Its energy output fluctuates in a rhythmic, almost musical pattern. This star pulses with a regularity that's almost too precise to be natural, leading some to speculate about the possibility of external influences, such as interactions with nearby stars or even the presence of unseen objects in its vicinity. The rhythmic pulses have been compared to the ticking of a cosmic clock, raising questions about what could be driving such precise oscillations. The causes of these unusual radiation patterns are still a subject of intense study. One leading theory suggests that the stars in this system are interacting in ways that amplify or distort their natural radiation emissions. For example, the gravitational pull of one star might be influencing the magnetic fields of another, creating feedback loops that result in these strange patterns. Another possibility is that the stars are surrounded by dense clouds of charged particles, which could be altering the way radiation escapes into space. These clouds might act like cosmic filters, bending and reshaping the radiation in unexpected ways. The implications of these findings are profound. If stars can emit radiation in such unpredictable and varied patterns, it could change how we interpret data from other star systems. For instance, what we once thought were stable stars might actually be undergoing similar processes, hidden from our view. This could have far-reaching consequences for our understanding of stellar evolution, as well as for the search for habitable planets. After all, unusual radiation patterns could affect the conditions necessary for life, either by creating harmful environments or by providing unique energy sources. This Undecuple system also raises questions about the broader universe. Are these unusual radiation patterns unique to this system, or are they more common than we realize? Could they be a sign of new stellar phenomena that we've yet to discover? As astronomers continue to study this system, they hope to uncover answers that could shed light on these questions and more. As we move forward, we'll explore another Undecuple system where stars are surrounded by glowing nebulae, creating a breathtaking cosmic spectacle. What secrets do these nebulae hold, and how do they shape the stars within them? Stay with us as we continue our journey through the mysteries of the universe. Now, let's shift our gaze to an Undecuple star system that exists within the remnants of a cataclysmic event, a supernova. This system, nestled in the aftermath of a star's explosive death, offers a rare glimpse into the chaotic and transformative processes that shape the cosmos. The stars here are not just survivors of a violent past, they are active participants in a dynamic environment that continues to evolve. The supernova remnant surrounding this Undecuple system is a sprawling cloud of gas and dust glowing with the energy of the explosion that created it. This remnant is not just a static relic, it's a vibrant, ever-changing structure that interacts with the stars within it. The intense radiation and shock waves from the supernova have left an indelible mark on the system, influencing the behavior and evolution of its 11 stars. One of the most striking features of this system is how the stars interact with the remnant. The shock waves from the supernova have compressed the surrounding gas, triggering new waves of star formation. Some of the stars in this Undecuple system are relatively young, born from the ashes of the explosion. These younger stars are surrounded by dense clouds of material which are still collapsing and forming new stellar bodies. This process creates a fascinating mix of old and new stars, each telling a different part of the story of this system's history. The older stars in the system, those that predate the supernova, have been profoundly affected by the explosion. The intense radiation and high-energy particles from the supernova have stripped away some of their outer layers, altering their composition and structure. These stars now shine with a different light, their spectra revealing the traces of the elements forged in the supernova. This interaction between the stars and the remnant provides valuable insights into how such events can reshape entire star systems. The supernova remnant also plays a crucial role in shaping the environment of the system. The gas and dust within the remnant act as a cosmic laboratory where complex chemical reactions occur. These reactions produce a variety of molecules, some of which are essential building blocks for life. The remnant's turbulent environment also generates powerful magnetic fields, which can influence the motion of charged particles and the behavior of the stars themselves. The ongoing effects of the supernova are not limited to the stars. The remnant's shockwaves continue to propagate through space, colliding with other interstellar material and creating regions of intense heat and pressure. These regions can trigger further star formation, perpetuating the cycle of stellar birth and death. The remnant itself is slowly dissipating, its material spreading out into the surrounding space, but its influence will be felt for millions of years to come. This Undecuple system offers a unique opportunity to study the aftermath of a supernova and its long-term effects on a star system. By observing how the stars and the remnant interact, astronomers can gain a deeper understanding of the processes that drive stellar evolution and the life cycles of stars. It also raises intriguing questions about the resilience of star systems in the face of such catastrophic events. Can life emerge or survive in such environments, or are they too hostile? The answers to these questions could reshape our understanding of the universe. As we move forward, we'll explore another Undecuple system where stars are surrounded by dark matter, a mysterious substance that makes up most of the universe's mass. What role does dark matter play in shaping these stars, and how does it influence their behavior? Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's turn our attention to an Undecuple star system where the stars are caught in a tempest of magnetic chaos. This system is home to some of the most intense magnetic storms ever observed, creating a dynamic and unpredictable environment that challenges our understanding of stellar behavior. These magnetic storms are not just fleeting disturbances, they are powerful, long-lasting events that shape the lives of the stars and the space around them. The magnetic storms in this system are driven by the complex interplay of the stars' magnetic fields. Each of the 11 stars has its own magnetic field, and when these fields interact, they can become twisted and tangled, leading to explosive releases of energy. These releases manifest as massive magnetic storms, which can last for days, weeks, or even longer. The storms are so intense that they can be detected from vast distances, their signatures visible in the form of bursts of radio waves and X-rays. One of the most fascinating aspects of these storms is their impact on the stars themselves. The intense magnetic activity can cause the stars' surfaces to become highly unstable, with massive flares and eruptions of plasma. These eruptions can hurl material into space at incredible speeds, creating a turbulent environment around the stars. The constant bombardment of high-energy particles can strip away the outer layers of the stars, altering their composition and structure over time. The effects of these magnetic storms extend far beyond the stars themselves. The storms generate powerful shock waves that ripple through the surrounding space, colliding with the interstellar medium and creating regions of intense heat and pressure. These regions can trigger new waves of star formation, perpetuating the cycle of stellar birth and death. The storms also produce intense radiation, which can ionize the surrounding gas and dust, creating glowing nebulae that light up the system. The magnetic storms in this Undecuple system also have profound implications for any planets that might exist within it. The intense radiation and high-energy particles produced by the storms would make it extremely difficult for life to survive on any nearby planets. The constant bombardment of charged particles would strip away any protective atmospheres, leaving the planets exposed to the harsh conditions of space. This raises intriguing questions about the potential for life in such extreme environments and the resilience of planetary systems in the face of such challenges. Studying these magnetic storms provides valuable insights into the behavior of stars and the processes that drive their evolution. By observing how the stars in this system interact with their magnetic fields, astronomers can gain a deeper understanding of the forces that shape the cosmos. It also highlights the incredible diversity of stellar phenomena and the complex interplay of forces that govern the universe. As we continue our journey through the mysteries of Undecuple star systems, we'll next explore a system where stars are surrounded by vast swarms of comets. What role do these comets play in the evolution of the system, and how do they interact with the stars? Stay with us as we uncover more cosmic wonders. Now, let's venture into a truly mesmerizing Undecuple star system, one where the stars are encircled by vast swarms of comets. These icy wanderers, numbering in the hundreds of thousands, create a breathtaking cosmic dance around their stellar hosts. But where do these comets come from, and what role do they play in the life of this extraordinary system? The origins of these comet swarms can be traced back to the early days of the system's formation. As the stars and their surrounding planets took shape, vast reservoirs of icy debris were left over from the process. Over time, gravitational interactions between the stars and their planets scattered this debris into elongated orbits, forming the swarms we see today. These comets are not just remnants of the past, they are active participants in the system's ongoing evolution. The behavior of these comets is shaped by the complex gravitational forces at play in an Undecuple system. With 11 stars exerting their pull, the comets follow highly irregular paths, often being flung from one star's influence to another. This chaotic motion creates a dynamic environment where comets can collide, break apart, or even be ejected from the system entirely. Some comets, however, settle into stable orbits around individual stars, forming dense clouds that can persist for millions of years. One of the most striking features of these comet swarms is their interaction with the stars themselves. As comets pass close to a star, the intense heat causes their icy surfaces to vaporize, creating glowing tails of gas and dust. These tails can stretch for millions of kilometers, painting the system with streaks of light. In some cases, the sheer number of comets creates a continuous haze around the stars, obscuring their light and creating a surreal, otherworldly glow. The presence of these comet swarms also has significant implications for the system's planets. Comets are often rich in water and organic compounds, and their collisions with planets can deliver these essential ingredients for life. However, the constant bombardment of comets can also pose a threat, disrupting planetary atmospheres and potentially triggering mass extinctions. This delicate balance between creation and destruction highlights the intricate interplay of forces in this Undecuple system. Studying these comet swarms offers valuable insights into the processes that shape planetary systems. By observing how comets interact with stars and planets, astronomers can better understand the conditions that lead to the formation of habitable worlds. It also raises fascinating questions about the potential for life in systems with such extreme dynamics. As we move forward, our next discovery takes us to an Undecuple system where stars exhibit strange and unpredictable light variations. What causes these fluctuations, and what do they reveal about the nature of these stellar giants? Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's turn our attention to an Undecuple star system where the stars themselves seem to play a cosmic game of hide and seek. In this system, the stars exhibit unusual light curves, their brightness fluctuating in ways that defy conventional explanations. These strange variations have left astronomers both puzzled and fascinated, as they hint at processes that challenge our understanding of stellar behavior. The light curves of these stars are anything but ordinary. Instead of the steady, predictable brightness we often associate with stars, these Undecuple stars flicker, dim, and brighten in irregular patterns. Some stars experience sudden, dramatic drops in brightness, while others show gradual, almost rhythmic changes. These fluctuations are not random. They follow distinct patterns that suggest underlying mechanisms at work. One possible explanation for these unusual light curves lies in the complex gravitational interactions within the system. With 11 stars orbiting one another, the gravitational forces are immense and constantly shifting. These forces can distort the shapes of the stars, causing them to stretch and compress in ways that alter their brightness. In some cases, stars may even pass in front of one another, creating eclipses that temporarily block their light from our view. Another intriguing possibility is that these stars are surrounded by massive clouds of dust and gas. As these clouds move and shift, they can obscure the stars, causing their light to dim. Over time, the clouds may dissipate or be blown away by stellar winds, allowing the stars to shine brightly once again. This interplay between the stars and their surrounding material creates a dynamic environment where light levels are constantly in flux. The observational significance of these unusual light curves cannot be overstated. By studying these variations, astronomers can gain valuable insights into the internal structure and behavior of the stars themselves. For example, the rhythmic pulsations of some stars may reveal details about their internal oscillations, much like how seismic waves provide information about the Earth's interior. Similarly, the sudden drops in brightness could indicate the presence of massive star spots or other surface features that block light. These light variations also offer clues about the broader dynamics of the system. By tracking how the brightness changes over time, astronomers can map the orbits of the stars and the distribution of dust and gas within the system. This information helps to build a more complete picture of how Undecuple systems form and evolve, shedding light on the processes that shape these cosmic wonders. As we continue our journey through the mysteries of Undecuple star systems, our next discovery takes us to a system located in the galactic halo, far from the bustling center of the galaxy. What secrets does this isolated system hold, and how does its environment shape the stars within it? Stay with us as we explore the unique characteristics of this distant cosmic outpost. Now, let's venture into the outer reaches of the galaxy, where an Undecuple star system resides in the galactic halo, a region far removed from the dense star-filled core. This system, isolated and shrouded in mystery, offers a stark contrast to the bustling environments we've explored so far. The galactic halo is a sparse, diffuse region that surrounds the main body of the galaxy, and the stars here exist in near solitude, separated by vast distances. This isolation shapes the system in ways that are both fascinating and unique. One of the most striking features of this Undecuple system is its extreme remoteness. Unlike star systems in the galactic disk, which are often influenced by the gravitational pull of neighboring stars and interstellar material, this system exists in a near vacuum. The stars here are so far apart that their gravitational interactions are minimal, creating a serene and stable environment. This isolation has allowed the stars to evolve in ways that are distinct from their counterparts in more crowded regions of the galaxy. The stars in this system are also remarkably old, dating back to the early stages of the galaxy's formation. These ancient stars are composed of primordial elements such as hydrogen and helium, with very few heavier elements like iron or carbon. This lack of heavier elements, known as low metallicity, gives these stars a unique chemical signature that provides valuable insights into the conditions of the early universe. Studying these stars is like looking through a cosmic time capsule, offering a glimpse into the galaxy's infancy. Another intriguing aspect of this system is its motion. Stars in the galactic halo often follow highly elliptical orbits that take them far above and below the galactic plane. This means the stars in this Undecuple system are on a perpetual journey, sweeping through the halo in long, looping paths. These orbits are influenced by the gravitational pull of dark matter, which is thought to dominate the halo region. The presence of dark matter not only shapes the star's trajectories, but also adds another layer of mystery to this already enigmatic system. The isolation of this system also has implications for its potential to host planets. While the lack of nearby stars reduces the risk of gravitational disruptions, it also means there is less material available for planet formation. However, the presence of ancient, low metallicity stars raises intriguing questions about the types of planets that could form here. Could these stars host rocky worlds with unique compositions, or are they destined to remain solitary beacons in the galactic outskirts? As we continue to unravel the secrets of this Undecuple system, we gain a deeper appreciation for the diversity of star systems in our galaxy. From the chaotic interactions of densely packed systems to the serene isolation of the galactic halo, each discovery expands our understanding of the cosmos. Next, we'll explore a system where stars emit powerful jets of material, carving out their own paths through the interstellar medium. What drives these dramatic outflows, and what do they reveal about the stars themselves? Stay tuned as we uncover the next chapter in our journey through the wonders of Undecuple star systems. Now, shifting our gaze to a system where cosmic fireworks light up the void, we encounter an Undecuple star system where stars unleash powerful jets of material into the surrounding space. These jets, often stretching for light years, are not just spectacular to observe but also hold vital clues about the inner workings of these stars. Unlike the serene isolation of the galactic halo, this system is a dynamic arena where stellar forces carve out their own paths through the interstellar medium. The formation of these jets is a fascinating process, driven by the intense magnetic fields and rapid rotation of the stars. As material from the star's surface or surrounding disk is accelerated to near light speeds, it is funneled along the star's magnetic poles and ejected into space. These jets can carry immense amounts of energy, often outshining the star itself in certain wavelengths of light. The result is a breathtaking display of cosmic power, as streams of charged particles and radiation shoot out in opposite directions. But these jets are more than just a visual spectacle. They play a crucial role in shaping the surrounding environment. As the jets collide with interstellar gas and dust, they create shock waves that heat the material and trigger the formation of new stars. In some cases, the jets can even carve out vast cavities in the interstellar medium, clearing the way for future stellar nurseries. This interplay between the jets and their surroundings highlights the interconnected nature of cosmic processes, where the actions of one star can influence an entire region of space. One of the most intriguing aspects of these jets is their variability. Some stars emit jets sporadically, with bursts of activity followed by long periods of quiet. Others produce steady streams of material that persist for thousands of years. This variability provides astronomers with a unique opportunity to study the mechanisms behind jet formation and the conditions that trigger their release. By observing these changes, scientists can gain insights into the internal dynamics of the stars, including their magnetic fields, rotation rates, and accretion processes. The impact of these jets extends beyond their immediate surroundings. The material ejected by the jets can travel vast distances, enriching the interstellar medium with heavy elements forged in the hearts of stars. This process, known as stellar feedback, plays a key role in the chemical evolution of galaxies. Over time, the material from these jets can become part of new stars, planets, and even life itself, creating a cosmic cycle of creation and destruction. As we explore this Undecuple system, we are reminded of the incredible diversity of stellar phenomena. From the serene isolation of the galactic halo to the explosive energy of jet-emitting stars, each discovery deepens our understanding of the universe. Next, we'll turn our attention to a system where stars are shrouded in dark molecular clouds, their light obscured by dense veils of gas and dust. What secrets lie hidden within these cosmic shadows? Stay with us as we continue our journey through the mysteries of Undecuple star systems. Now, let's venture into a system cloaked in mystery, where stars are veiled by dark molecular clouds. These dense, shadowy formations are not just cosmic curtains, but intricate structures that play a vital role in the life cycle of stars. Imagine a stellar neighborhood where the light of Undecuple stars struggles to pierce through thick layers of gas and dust, creating an eerie yet fascinating environment. Dark molecular clouds are composed primarily of hydrogen molecules, along with traces of other elements like carbon, oxygen, and nitrogen. These clouds are incredibly cold, with temperatures often dropping to just a few degrees above absolute zero. This frigid environment allows molecules to clump together, forming the building blocks for future stars and planetary systems. Despite their name, these clouds are not entirely dark. They emit faint radio waves and infrared light, which astronomers use to study their structure and composition. The presence of these clouds has profound effects on the stars they surround. For one, they act as cosmic incubators, shielding young stars from the harsh radiation of their older siblings. This protection allows protostars to grow and gather mass without being disrupted. However, the clouds also obscure the light from these stars, making them difficult to observe in visible wavelengths. To study these hidden stellar systems, astronomers rely on instruments that detect infrared and radio emissions, peeling back the layers of darkness to reveal the secrets within. One of the most intriguing aspects of these clouds is their role in star formation. As gravity pulls the gas and dust together, regions within the cloud begin to collapse, forming dense cores. These cores eventually ignite, giving birth to new stars. The process is slow and delicate, often taking millions of years. Yet, once a star is born, its radiation and stellar winds begin to erode the surrounding cloud, carving out cavities and shaping the interstellar medium. This interplay between creation and destruction is a hallmark of these systems, showcasing the dynamic nature of the cosmos. But the influence of dark molecular clouds extends beyond star formation. They also serve as cosmic laboratories where complex molecules can form and interact. Within these clouds, scientists have detected organic compounds, including amino acids, the building blocks of life. While these molecules are not evidence of life itself, their presence suggests that the ingredients for life may be widespread throughout the universe. This raises tantalizing questions about the potential for life in other star systems, even those shrouded in darkness. As we explore this Undecuple system, we are reminded of the delicate balance between light and shadow in the universe. The dark molecular clouds may obscure the stars, but they also nurture them, playing a crucial role in the cosmic cycle of birth and renewal. Next, we'll turn our attention to a system where stars generate unique gravitational waves rippling through the fabric of space-time. What mysteries do these waves hold? Stay with us as we continue our journey through the wonders of Undecuple star systems. Now, let's shift our gaze to a system where the very fabric of space-time is set into motion by the dance of its stars. In this Undecuple star system, the stars are not just luminous bodies but powerful generators of gravitational waves, ripples that travel through the cosmos, carrying secrets of their origins and interactions. These waves, first predicted by Albert Einstein over a century ago, are not just theoretical curiosities. They are real, detectable, and full of cosmic significance. Gravitational waves are created when massive objects like stars or black holes accelerate or collide, sending ripples through spacetime itself. In this Undecuple system, the stars are so massive and their orbits so dynamic that they produce gravitational waves with unique signatures. Unlike the more common waves detected from binary black hole mergers, these waves are shaped by the complex gravitational interplay of 11 stars, each pulling and pushing on the others in a cosmic ballet. The result is a symphony of spacetime ripples, each wave carrying a distinct pattern that tells the story of the system's evolution. Detecting these waves is no small feat. Gravitational waves are incredibly faint by the time they reach Earth, requiring highly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, to pick up their signals. In this system, the waves are particularly challenging to detect because of their irregular patterns and the sheer number of stars involved. However, advancements in technology and data analysis have allowed astronomers to isolate these unique signals, offering a glimpse into the inner workings of this extraordinary system. The significance of these gravitational waves goes far beyond their detection. They provide a new way to study the stars themselves, revealing details about their masses, orbits, and even their internal structures. For example, the waves can show how stars in the system interact gravitationally, whether they are locked in tight orbits or drifting apart over time. They can also reveal the presence of hidden objects like black holes or neutron stars that might otherwise go unnoticed. In this way, gravitational waves act as cosmic messengers, delivering information that light alone cannot provide. One of the most fascinating aspects of this system is how the gravitational waves influence the stars themselves. As the waves ripple outward, they carry away energy, causing the stars' orbits to gradually change. Over millions of years, this process can lead to dramatic shifts in the system's structure, potentially causing stars to collide or merge. These events, in turn, generate even more gravitational waves, creating a feedback loop that shapes the system's future. It's a reminder that even in the vastness of space, everything is connected, and every action has a reaction. The discovery of these unusual gravitational waves also has broader implications for our understanding of the universe. By studying them, scientists can test the limits of Einstein's theory of general relativity, exploring how gravity behaves in extreme environments. They can also learn more about the formation and evolution of complex star systems, shedding light on how Undecuple systems like this one come to exist. Each wave is a piece of the puzzle, helping us build a more complete picture of the cosmos. As we reflect on this system, we are reminded of the incredible power of gravitational waves to unlock the secrets of the universe. They are not just ripples in space-time, they are windows into the heart of some of the most mysterious and dynamic systems in existence. Next, we'll explore a system that lies within a dwarf galaxy, a place where isolation and uniqueness collide. What wonders await us there? Stay tuned as we continue our journey through the strange and fascinating world of Undecuple star systems. Now, let's venture into a realm where the stars shine in solitude, far from the bustling heart of the Milky Way. This Undecuple star system is nestled within a dwarf galaxy, a small, faint cosmic neighbor that orbits our own galaxy. Dwarf galaxies are often overlooked, but they are treasure troves of unique stellar phenomena, and this system is no exception. Its isolation from larger galactic structures gives it a distinct character, offering astronomers a rare opportunity to study Undecuple systems in an environment free from the gravitational chaos of more crowded regions. The dwarf galaxy hosting this system is a faint, diffuse collection of stars, gas, and dark matter, spanning only a fraction of the size of the Milky Way. Its small size and low density mean that interactions between stars are less frequent, allowing this Undecuple system to evolve in relative peace. Unlike systems in larger galaxies, which are often disrupted by nearby stars or passing black holes, this one has remained stable for billions of years, preserving its intricate gravitational dance. One of the most striking features of this system is its composition. The stars here are older and more metal-poor than those found in larger galaxies, a relic of the early universe when dwarf galaxies were among the first structures to form. These ancient stars provide a window into the conditions of the cosmos shortly after the Big Bang, offering clues about how the first stars and galaxies came to be. Their low metal content also affects their behavior, making them burn cooler and last longer than their metal-rich counterparts. The isolation of this system has another fascinating consequence. It allows astronomers to study the gravitational interactions between its stars with unparalleled clarity. Without the interference of nearby stars or dense gas clouds, the orbits of the 11 stars can be mapped with remarkable precision. This has revealed a complex web of gravitational influences, with some stars locked in tight binary pairs while others drift in wider, more irregular orbits. The system's stability over billions of years suggests that these orbits are finely balanced, a testament to the delicate equilibrium that governs such complex systems. But what truly sets this system apart is its role in the larger cosmic story. Dwarf galaxies like this one are thought to be the building blocks of larger galaxies, merging over time to form the majestic spirals and ellipticals we see today. By studying this Undecuple system, scientists can gain insights into how such mergers occur and how they shape the evolution of galaxies. It's a glimpse into the past, present, and future of galactic formation, all contained within this small, isolated corner of the universe. As we ponder this system, we are reminded of the incredible diversity of the cosmos. Even in the quietest, most remote places, the universe continues to surprise us with its complexity and beauty. Next, we'll turn our attention to a system where stars emit intense X-rays, a phenomenon that challenges our understanding of stellar behavior. What secrets do these high-energy emissions hold? Stay with us as we uncover more mysteries of Undecuple star systems. Now, let's shift our gaze to a system where the stars themselves seem to defy the norms of stellar behavior. In this Undecuple star system, the stars emit intense X-rays, a phenomenon that has left astronomers both puzzled and fascinated. X-rays are typically associated with extreme environments, such as the regions around black holes or neutron stars, but here they are being produced by ordinary stars in ways that challenge our understanding of stellar physics. The X-ray emissions from these stars are unusually strong, far exceeding what would be expected from stars of their size and age. This has led scientists to investigate the underlying causes, which appear to be linked to the stars' magnetic fields and their interactions with one another. In this system, the stars are not just passively orbiting. They are actively influencing each other's magnetic environments, creating conditions ripe for high-energy emissions. The tangled magnetic fields between the stars can accelerate particles to incredible speeds, causing them to emit X-rays as they collide or spiral along the magnetic lines. But what makes this system even more intriguing is the impact these X-rays have on the surrounding space. The intense radiation bathes the entire system, affecting any planet's dust or gas that might be present. Planets orbiting these stars would be subjected to a constant barrage of high-energy radiation, which could strip away their atmospheres or make them uninhabitable. This raises questions about the potential for life in such extreme environments and how planetary systems might evolve under such harsh conditions. The X-ray emissions also provide a unique opportunity for astronomers to study the dynamics of the system. By observing how the X-rays vary over time, scientists can map the interactions between the stars and their magnetic fields. This has revealed a complex dance of energy and matter, with some stars acting as dominant sources of X-rays while others contribute to the overall radiation in more subtle ways. These observations are helping to refine our models of stellar behavior, particularly in multi-star systems where gravitational and magnetic forces intertwine. As we explore this system, we are reminded that the universe is full of surprises. Even in systems that seem ordinary at first glance, there are hidden layers of complexity waiting to be uncovered. The intense X-ray emissions from these stars not only challenge our understanding of stellar physics, but also open new avenues for exploring the interactions between stars and their environments. Next, we'll delve into a system where stars are orbited by structures that defy natural explanations, sparking theories about extraterrestrial life. What could these mysterious structures be? Stay with us as we uncover the final discovery in our journey through the strange and wondrous world of Undecuple star systems. Now, let's turn our attention to what might be the most mind-bending discovery of all, a system where stars are encircled by structures so bizarre they defy all natural explanations. In this Undecuple star system, astronomers have detected massive, artificial-looking formations orbiting several of the stars, sparking intense speculation about the possibility of extraterrestrial intelligence. These structures, often referred to as alien megastructures, are unlike anything observed in nature, with their precise geometric shapes and unnatural patterns of light absorption. The most striking feature of these megastructures is their ability to block significant amounts of starlight in irregular intervals. This phenomenon, first noticed through dips in the star's brightness, doesn't match the predictable patterns caused by planets or dust clouds. Instead, the light curves suggest the presence of enormous, engineered objects perhaps designed to harness energy from the stars themselves. Theories range from Dyson spheres, hypothetical structures built to capture a star's energy, to even more advanced constructs that might serve purposes beyond our current understanding. What makes this discovery even more fascinating is the scale of these structures. They are not small or localized, they are colossal, spanning distances that dwarf even the largest planets. The sheer size and complexity of these formations imply a level of technological advancement far beyond anything humanity has achieved. This has led some scientists to propose that we might be looking at the work of a Type II civilization on the Kardashev scale, a civilization capable of harnessing the energy of an entire star. But the implications don't stop there. The presence of these megastructures raises profound questions about the nature of life in the universe. If such advanced beings exist, what are their goals? Are they observing us, or are we simply witnessing the remnants of a long-gone civilization? The possibility of contact, or even the mere existence of such intelligence, challenges our understanding of our place in the cosmos. As we ponder these questions, it's worth noting that this discovery also pushes the boundaries of astronomy itself. The search for alien megastructures has become a new frontier in the study of exoplanets and stellar systems. By analyzing the light curves and other data, scientists hope to uncover more clues about these mysterious objects and perhaps find evidence of other civilizations among the stars. This Undecuple star system, with its enigmatic megastructures, serves as a powerful reminder of how much we have yet to learn about the universe. It invites us to dream bigger, to question our assumptions, and to remain open to the possibility that we are not alone. As we conclude our journey through these 50 strange discoveries, one thing is clear: the cosmos is far more mysterious and wondrous than we ever imagined. What other secrets lie hidden among the stars? The search continues, and the answers may be closer than we think. As we wrap up our exploration of these 50 strange discoveries about Undecuple star systems, one thing becomes undeniably clear: the universe is a place of endless wonder and mystery. From the first detection of an Undecuple system to the mind-bending possibility of alien megastructures, each discovery has pushed the boundaries of what we thought was possible. These systems challenge our understanding of star formation, gravitational dynamics, and even the potential for life beyond our solar system. They remind us that the cosmos is far more complex and unpredictable than we could have ever imagined. These findings don't just expand our knowledge, they ignite our curiosity. They force us to rethink our assumptions about how stars and planets form, how they interact, and what might exist in the vast, uncharted regions of space. Whether it's a system with stars of vastly different ages, a black hole lurking among its members, or the eerie glow of stars with unusual atmospheres, each discovery adds a new piece to the puzzle of the universe. And yet, for every question answered, a dozen more arise, inviting us to dig deeper and explore further. So, what does all of this mean for us? It means that the universe is still full of secrets waiting to be uncovered. It means that every strange discovery, no matter how small or bizarre, brings us one step closer to understanding our place in the cosmos. And it means that the search for knowledge is far from over. As we continue to peer into the depths of space, who knows what other wonders we might find? Now, it's your turn to join the conversation. What do you think about these strange Undecuple star systems? Do you believe we'll one day find definitive proof of extraterrestrial intelligence? Or are these megastructures just another cosmic mystery waiting to be solved? Share your thoughts in the comments below. We'd love to hear your ideas and theories. And if you're as fascinated by these cosmic wonders as we are, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an update. The universe is vast, and the journey to understand it has only just begun. Let's keep exploring together.